Hi. Till now, we have developed many small projects in VHDL and integrated them on FPGA board as well. Now, from this session, we will develop little complex VHDL design, and we will develop this using multiple VHDL modules. We are developing a UART module with transmitter and receiver with flexible baud rate. In this session, we will understand the idea behind the UART module, and then from the next session, we will start developing it in multiple parts. Like one part is Baud Clock Generator, one part is transmitter, one part is receiver, one part is serializer, like that. And we will also write test benches to test our designs. So this is the block diagram of a simple UART module. In the left hand side, we have our UART transmitter, for example, our PC, which is sending data. So you see this box here. Suppose this is your PC, and this small box here is your UART port or serial port in your PC. Now, in this right hand side, we have that same UART port or serial port. But now this is from your FPGA board. So you will see this serial port in your FPGA board. So we will get the data at this port, and then this data will be processed with the finite state machine in FPGA. We will talk about this finite state machine system sometime later. So this UART port from PC sending serial data, and this UART port at the FPGA port is receiving that serial data through this data lines. And once this UART receiver receives a valid character, then it will pass this data to this finite state machine. So this state machine will detect the character, and suppose it is again sending it back to the PC. Means now this UART port from the FPGA will act as a transmitter and PC will act as a receiver, and the data will flow through this data line. So it is a kind of a loop back application what we are designing. So we will design the system in VHDL, and then we will simulate it on Model Sim Simulator. Now, because this design is complex, so we will break down this in the individual module, and we will also design and test them individually. Like we will break down this UART transmitter into serializer and Baud Clock Generator. We will separately design this state machine. We will split UART receiver into shift register and Baud Clock Generator, etc. So there will be multiple modules we will be designing for this project. Okay, so let's talk about the UART transmitter first and see how we will design this. So here we are break down our UART transmitter into these two modules. This first block is a serializer block. So what it will do that it will convert 8-bit parallel data into serial data so that they can transmit over a single bit data line, because UART is a serial communication protocol and data can only transfer one by one. So we need this serializer to convert input 8-bit data into serial single bit stream. So we will write a VHDL code for this serializer. You can see this serializer has three inputs: DIN, load, and shift enable, and it has one output, DOut. Now DOut is a serial output, so it is single bit output. But DIN is a parallel data, and say it is 8-bit. However, it can have any length, like it can be 4-bit or 10-bit or 16-bit, etc. Now this load input. So it will be asserted whenever we have a valid data at this input port DIN. Means whenever this load signal is asserted, our parallel data present at this DIN port will be captured by this serializer. Now we have this additional input as well. This is shift enable, and this is very important for UART communication, because we cannot send this serial data which is coming out from this DOut port at any speed or at any bit rate. we need to be very careful that when the serial data will transfer to the transmission line, means we need to decide that when exactly we need to get serial data output. And for that, we need this shift enable pin. This shift enable pin will tell the exact time when your bit data should be shifted out from this serializer. We need this stringent timings because RS-232 protocol, which is used by this UART system, means UART transmitter and UART receiver, has some very specific bit rate. So we need to make sure that all the transmissions and the reception must follow these supported bit rates. So this shift enable pin will control all these things for us. Do not worry, we will see that how it happens and how it works. And we will design this as well. But in brief, we have this second module here, and this module will generate this shift enable functioning in our design. We will call this Baud Clock Generator, and its output will be used as a shift enable pin for this serializer. Means you can say that this Baud clock output is connected to this shift enable pin of this serializer in our UART module, but we will design them as a separate units. Means we need to design this baud clock output to synchronize with very specific baud rate because it will drive the shifting operation of this serializer. So it will generate the pulses to shift out data based on very specific timing control, which we will call 1 bit period. So this is just high level. We will design it in VHDL little later. So we can see that this Baud clock generator has start input and ready output, and of course Baud clock output. Now what this start input will do. To understand this, let's see what this Baud clock generator is doing. So it will generating pulses to allow the serializer to shift data to the output one by one and at very specific time bit period. Now suppose we have 8 bits at this input of serializer. Means we need 8 pulses to shift 8 bit of data, right? So this start input will tell that exactly when these pulses should start. Means for our example of 8-bit data, this Baud clock generator will generate 8 pulses after this start input is asserted. Now we have one additional put, and that is output ready. Once this Baud clock generator generates 8 pulses for our serializer, then it stops generating more pulses because we do not need them after data transfer is complete, right? So once this 8 pulse generation is completed, this ready output will be high. This means that our 8-bit data is transmitted and we are ready for transmitting the next data. And for this time, our Baud clock generator will stop generating any pulses until next start signal is asserted. Means after ready signal is high, it will wait for this start signal. And when this start signal is asserted, this Baud clock generator will repeat the steps, means it will generate 8 pulses to shift 8-bit data once again. And for that time, this ready output will be low. And once it completes 8 pulses and the 8-bit data is transmitted, then this ready output will be high again. Okay, so this is our UART transmitter module. And next will be UART receiver module. So let's see this in the next slide. So this is the block diagram of UART receiver. Your input data will come through this RX input. Now this input will pass through this synchronizer and you will get D in as an input. Now we need this synchronizer because we can get this RX input at any point of time. Means this input is asynchronous to the internal clock of FPGA board. So if you use this RX signal without this synchronizer, we can have stability problems in our designs, which is not good for a reliable design, right? So to avoid these issues, we will convert this asynchronous signals into a synchronous signals. So we have this synchronizer in between, and the output of this synchronizer is exactly same as this RX signal, but it is delayed by some clock pulses. Means this DIN has the same data as the RX signal, but it is now synchronized with the FPGA clock frequency. And we will use this DIN as a data input to our UART receiver instead of this RX input. Okay. Next, we will move this DIN signal into a shift register. Why? Because this DIN signal is a serial data which is received over the single bit transmission channel. And to recover the data, we need to convert this serial data into parallel data. So this shift register module will capture the serial data and then it will convert it into 8-bit output data, which is D out here. So this is our shift register, which will convert serial data into parallel data, right? Now you will see that this serial data is also connected to this start bit detector module as well. And what it will do that it will detect the signal whenever a new message or a new data is received by this UART receiver. Now there are some protocol standards of RS-232 protocol. And one important standard is that when RS-232 is ideal, means when it is not transferring any data, then this signal remains at logical high. And when data transmission is ready, then the first bit will be always logical 0. Means when data is not transferring, we have logical high. And when data is ready to transmit, then the first bit will be logical low. So simply, we will look for logical 0 to detect if any data is transmitting or not. Means we will look for the falling edge of this DIN signal. And when this falling edge is detected after the ideal state, we will say that there is some data is transferring. Means we detect a start bit through this start bit detector module. And once this start bit is detected, it will trigger this Baud Clock Generator. So this is a separate Baud Clock Generator module. We discussed this in the last slide as well for UART Transmitter section. So this Baud Clock Generator will generate similar pulses to drive this shift register, and it will generate pulses based on the number of input bits. Like we have this RX port here or DIN port here. And this Baud clock is connected to this shift enable pin of this shift register, just like it is connected to the serializer in UART transmitter section. So each time this Baud clock pulse is given, this DIN input will shift 1 bit into the shift register. So if you want to capture 8 bits, you required 8 pulses. And at each pulse, this shift register will capture 1 bit from this DIN input. And once you capture all the 8 bits, you will get 8-bit parallel data output to this output port D out. So that's complete our UART receiver module as well. In the next session, we will quickly brief RS-232 protocol, and then we will design it and test it in VHDL with real practical and simulation. In the last session, we talked about UART communication and we briefly introduced RS-232 protocol. Now, before designing this UART communication, we need to understand some important standards of RS-232 protocol. So we are covering them in this session. RS-232 is a communication protocol that is used to communicate between two devices. This communication happens serially, means your transmitter will transfer the data sequentially or 1 by 1 bit. And then receiver receives this serial data and later convert it into parallel data. So this is a simple block diagram of UART communication, which will use RS-232 protocol. So we have device 1, which is transmitting serial data, and we have device 2, which is receiving this serial data. Some way this device 2 can also send serial data to device 1 as well. So each device here has one transmitting module and one receiving module. And this combination is called a UART module. And the transmission method is using RS-232 protocol. Okay. Now this is the basic structure of RS-232 protocol. It is combined with four different blocks. First block is start bit. Second block is data bits. Third block is parity bit. And the fourth block is stop bit. So as I said, RS-232 protocol transmits logical high when it is idle. And for starting a data transfer, we need logical 0. So this first block, or we can say start bit, is always logical 0. Means if you are using RS-232 protocol and if you want to send any data through this protocol, then you need to send start bit first. And this will be logical 0. Next, come to this second block. So this is our data bits. Now RS-232 protocol supports 5 bit of data to 8 bit of data, but widely 8 bits are used. Now the third block is parity bit, and RS-232 protocol supports both even parity and odd parity bit, and it is an optional block, means depends on your requirement. Either you want to send it or not. And the last block is stop bit. And for RS-232 protocol, this stop bit will always logical high. And you can have either 1 bit or 1.5 bit or 2 bit for this stop bit. Now let's understand this with one simple example. So in this example, we are sending hex data 69 over this RS-232 protocol. So at the beginning, you can see that RS-232 line is idle and it is logical high. Next, we have start bit. So this is logical 0 here, and it will indicate that a new data is ready for transmission. Next, we have data bits. So in our case, it is 8-bit data. Now you need to remember that when you are using RS-232 protocol, you always send LSB first. Means your least significant bit will transmit first and your most significant bit will transmit last. Means bit index 0 will transmit first and bit index 7 will transmit last. Now after transmitting all of these 8-bit data, we send stop bit and it is always logical high. And finally, this signal remains high, or we can say at idle state. This means that no further data is about to transfer now. And if you want to send another data byte, then this process will repeat itself. Means first we will transmit start bit, followed by the data bits and then stop bit. Now this is the important topic in RS-232 protocol. As I said, we need to be very specific in timings to send our data. And this timing is decided by the baud rate. Basically, this baud rate is also referred as bit rate or data rate. And RS-232 protocol support these listed baud rate or bit rate, you can say. These listed numbers are the number of bits that can transfer within 1 second. So you can see that this top one is having the highest baud rate, and that is 115200. And at the bottom, we have lowest baud rate, that is 9600. And between them, we have 57600, 38400, 19200, and 14400 as well. You can choose any of this baud rate for your transmission. For example, if you want to use highest baud rate, that is 115200, then your bit period will be 1 divided by 115200, means 8.7 microseconds. This means that you have to transfer each bit at every 8.7 microseconds. Same way, you can choose any baud rate from this list, and accordingly, you can calculate your bit period for your transmission. Now, it is important that you can only select baud rate from this supported baud list only. This is RS-232 standards, and you cannot go beyond these protocol standards. So this was a brief about RS-232 protocol. Hope you understand it, because we are going to develop this in our next session. In the last session, we understand RS-232 protocol, and we learned about the standard baud rates as well. Now we are going to design this Baud Clock Generator in VHDL for our UART project. So let's understand how we will design this Baud Clock Generator for our project. And this is very important, that we generate pulses at correct timings when you are transmitting or receiving any bit over the RS-232 protocol. So this is a simple block diagram that what we are designing here. We have this baud clock as an output here. Inside this module, we have a counter. This is named as bit period counter, and it will increment at every rising edge of clock cycle, which is 50 megahertz suppose. Now we will compare this counter value with this bit period. This bit period is fixed for a specific baud rate, or you can say it is a constant value. Now, when our bit period counter value is equal to this bit period value, then we will trigger our baud pulse. And we will also reset our bit period counter to 0 to count another bit period for the next pulse. So this will happen again and again until all the bits are transmitted, right? And each time it will generate a pulse at this output baud clock. And the timings of this pulse will be controlled by this constant value, bit period. But here is a small problem, that if we design this system, it will generate pulses all the time, despite we are sending data or not. And we do not want this. What we want, that we want to generate only fixed number of pulses when we are transmitting data or receiving data. So we need some extra control signals for that. So what we need to tell that how many pulses we actually need for transmitting or receiving data. Now let's stick on the transmission of data first. Now for this purpose, we will create a clock counter like here, and it will count each generated pulse. We also need a trigger signal. For example, here we have start signal. Means when this start signal is asserted, we will load number of pulses to this clock counter. For example, we need 10 clock pulses. So when you assert this start signal, then this clock counter will load 10 as a counter value. And now as soon as a new pulse is generated from this baud clock, we will reduce one pulse from this value. So at the starting, it will say 10 pulses are needed. Then your first pulse will generate at this baud clock, and it will decrease this counter by value of 1. And now you have 9 pulses remaining. Now second pulse is generated at this baud clock, so your clock counter will decrement by 1 again. So it becomes 8 now. Basically, it is telling that how many pulses are remaining to generate. Okay, so we need to ensure that when this counter is 0, means we do not need any more pulses at this baud clock output. We should stop generating pulses at this baud clock output, right? So we need this additional check here, that we will only count bit period clock when our remaining pulses are greater than 0. Means this whole module will only work when you need pulses for transmitting of data. And for ideal time, it will not generate baud clocks. Now it looks little complicated. So let's brief it quickly. Let's consider that we are needing 10 pulses at baud clock when we start this module. So first we will trigger this start signal. When this start signal is asserted, then this clock counter will get 10 pulses, right? because we will load value 10 in this counter. Now this value is greater than 0. So this bit period counter will count every clock signal. And once it matches to the specified bit period, it will generate first baud clock pulse. And your first bit will start transfer. Okay. Now at the same time, it will decrease this clock counter value by -1. Means it is 9 now. Again, it is greater than 0. So this bit period counter will count for next pulse. And it will generate second pulse at this baud clock output. And also it will decrease this clock counter by 1. So now it is 8. Now this will happen 10 times. And when it will generate last pulse, this clock counter value become 0. Means now this condition is not met. So your bit period counter stops counting and no more pulse will generate at this baud clock generator. So this is the whole process. Now if you want to transmit another byte, then again you will trigger this start signal here and the whole process will run again. Okay, so if this is clear, then please try to design this in VHDL. If not, don't worry, we will be designing this in VHDL in the next session. In the last session, we understand the idea that how we are going to design Baud Clock Generator in VHDL for our UART project, which is using RS-232 protocol. So today we will write a VHDL code for this, and then we will simulate it with VHDL test benches. So quick brief, this is the block diagram of Baud Clock Generator. We will use 50 megahertz of clock frequency and we will generate the baud pulses at the baud rate of 115200. We will have this start signal to trigger this baud clock generator. And once start signal is asserted, then this baud clock generator will generate a fixed number of pulses at this baud clock output. And then it will go to the ideal state. We have explained this block diagram in complete details in our last session. So this is just an overview. If you want to understand what we are designing and how this block diagram is working, then please watch my last session. It is really important to understand the logic first. Okay, so let's write the VHDL code for this module. Okay, so first what we will do, we will open VHDL editor, but this time I will use Notepad++ to code my VHDL program. But you can use any VHDL editor which you want to use, okay? So you can see that I have opened this Notepad++ here and we will write our VHDL program in this editor today. So first we will save this file. So go to this File tab and click on Save As. Now I want to create a new project for this. So I will select some folder from here and I will create a new folder. Now I will give it some name. For example, this is UART project. Okay, so UART project. Now click enter. And this module is our Baud Clock Generator. Okay, so give it some name. Suppose I want to give it name Baud Clock Generator. Okay, because this is our Baud Clock Generator project, right? Now I want to save this file as a .vsd file. So I will click on Save As Type. Now I will search for basic file. So this is VHSIC file. So this is the basic hardware description language. Now I will select this and then click on Save. Now we will write our VHDL program here. So we will start from the library declaration. So give it library IEEE use IEEE dot std underscore logic underscore 1164 dot all. So you can see the benefit of saving this file as .vsd file, because you can see that all the keywords are highlighted with different colors, right? So if you don't save this file as in .vsd, then it will be look like a plain text. Let me zoom in this window so that you can see it very clearly. So this is our library declaration. Now the next is entity declaration. So write it entity Baud Clock Generator is now port declaration. So port, first we will declare the mandatory signals and these are clock and reset. So clock that is input type std underscore logic. Next is reset. So reset, that is in std underscore logic. So these two signals are very common signal for a registered process block. Now we will declare the other important ports for this module. So if you remember from our last session, we explained that we are needing three signals for this module. And these signals are start signal, Baud clock signal, and ready signal. And all these signals are std logic type. So declare them. So first we have this start signal, and this is input type and std underscore logic data type. Okay. Next we have output port. So that is Baud clock, and that is out std underscore logic. And we have one more output, and that is ready. So that is out again std underscore logic. Now bracket closed because all the ports are declared. And finally and entity. So and Baud Clock Generator, right? So this is our entity declaration. Next, we will define our architecture for this module. So first we will write the architecture body. So write it architecture behave of this Baud Clock Generator is now begin, and in the last and behave or and architecture. So this is the structure of architecture, and we have two sections here. So this section is for declaration, and this section after begin keyword is for your functional design, right? Now what we will do that we will write our VHDL program first, and then we will define the necessary signals and constant later. So this is my preferred way of designing. Although you can declare the signals or constant first and then write your VHDL program. But it is really difficult to think of all the signals required for your VHDL programs in the starting of your VHDL code. So first we will write our VHDL code, and then in the last we will declare all the signals and constant needed for this project, right? So let's start our VHDL program. So very first we will define this Baud clock output, because this is our main output of this module, and we will write a process to define this Baud clock output. Okay. So this is our Baud clock output here. Okay. And we are writing this process for this signal. Okay. Now start our process block. So first give it some name. For example, I'm giving this bit period process. This is a process, and clock and reset is in the sensitivity list because this is a registered process block. Now begin and end process. So this is a basic structure of a process block in VHDL. Now let's write the template for a register process block. So this is if reset is equals to 1, then do something. Else if at rising edge of clock, then do something, and in the last and if. So this is the basic template of a registered process block. Now first we will write what will happen at the rising edge of clock. So we will write a program here in this section. Now in the last session, we have explained that how this Baud clock output is generated and how we control the timings of this Baud clock signal output. So as we explained, we will use a simple counter, and we will count it at every rising edge of our system clock. And when this counter reaches to some specific point based on your selected baud rate, then it will give you the Baud clock pulse, and your counter will start counting from 0 again, right? So we will write the code for this logic. Suppose our counter name is bit period counter. Okay, so write it bit period counter. So that should be bit period counter plus 1, right? So this statement will increase the counter by 1 at every rising edge of your clock. Now we will define that when this increment will happen. So when it will happen if this bit period counter is less than some specific value, or you can say is equal to some specific value. For example, this specific value is 1000 or 2000, right? But as we said that RS-232 protocol only supports very specific baud rate. You cannot select any bit rate of your choices. So you have to stick on the RS-232 protocol standards, right? and this protocol supports few of the different baud rates. And I want to write a general VHDL code that can be used at any baud rate. Now I do not want to write a very specific VHDL code which can only work with a very specific system clock frequency and very specific baud rate. Instead, I want this code to run on any system clock frequency and any baud rate. So we will not hard code this value here. Instead, we will use the mathematical calculations. And for that, we will use a constant. So instead of this hard coded value here, we will use a constant. And suppose the constant is bit period. Don't worry because we will define all the signals and constant once we finish the architecture part of this VHDL code, right? So if bit period counter is equals to bit period, then what will happen? Then our counter should reset to 0, right? So this bit period counter should be 0, right? Else, what will happen? Else we will increase our counter at every rising edge, right? So this is correct. Now let's terminate this if condition as well. So and if, now we will drive this baud clock output within this process, right? So what will happen that every time this bit period counter match with this bit period that we will define, then we want to give a pulse to this output, right? Giving a pulse means for one clock cycle, the value of this baud clock is 1 and for rest of the time, the output will be 0, right? So write it. So if bit period counter is equals to bit period, then our baud clock output will be 1, right? Else what will happen? Our baud clock output will be 0. Okay. So this process it looks good and it is driving this baud clock output. Okay. Now let's give the reset condition as well, that what will happen when the reset is asserted. So our baud clock output will be 0, right? And our bit period counter will be 0 as well. Okay. So it's covered the reset condition as well. So this process looks good for this baud clock output. And now we will create another process to define that when this baud clock output will generate. Why? Because we want that this baud clock will only generate the pulses when there are some data to transfer. And for rest of the time, it will not generate any data or any pulses, right? So if we leave this process as it is, then it will continuously generate the baud clock output. And we do not want this. We want to control that when we give the start pulse to our this baud clock generator, then only it will generate the number of pulses. For example, if we want to transfer 8 bits, then it will generate 8 pulses. If we want to transfer 10 bits in total, for example, start bit, data bits, parity bit, or stop bits, then it will generate 10 bits. So we will write one another process to control this part of our module. Okay. So first we will give some name to this process block. Suppose this process is pulse control process. Okay. You can give any name, doesn't matter. And this is optional as well. So if you do not want to give any name to any of your process, then you can leave it as well. But if you're using many processes in your VHDL code, then it is always a good practice to name your process block so that you can know that this process is for what purpose, right? For example, our last process was for the baud clock output and we were generating the baud pulses based on our bit period counter. So we gave the relative name to that process, that is bit period process. Now this is pulse control process. So first we will write the basic template of a registered process block. So this is a process. Now clock and reset in the sensitivity list. Now begin and process. Next, if reset is equals to 1, then do something. Else if rising edge of clock, then do something, and in the last and if, right? So this is our basic template. Now what will happen that So we have this start as an input port here. So when this start pulse is given, our Baud clock generator will generate the number of pulses, right? So we need to define that how many pulses we need to give in. And that is depend on the data width, right? So what I will write that if this start signal is equals to 1 means when this start pulse is given, then what will happen? We will load the number of data bits to some internal signal. Suppose this internal signal is pulse pending. Okay, so number of pulses pending. So this is pulse pending that should be equal to your number of data bits. Suppose I want to give it some name, for example, data width. Now, because this data width can be different for your different projects or for your different requirements, because in RS-232 protocol, you can supply flexible number of bits. For example, 6 number of data bits or 7 number of data bits or 8 number of data bits. So it is totally depends on your project needs. So I will not hard code this. Instead, I will use a generic where we will define the data width of our signal. And then I can use this program for 8-bit data, for 6-bit data, or 7-bit data, etc. So always try to write a generic programs for your VHDL designs. So what I will do that I will define a generic for this data width, but I will do it little later. First, let's finish this VHDL program. So pulse pending gets a value of data width, and that will happen when start pulse is given, right? For example, consider the total data width is 10 bits. So we have to generate 8 pulses in the Baud clock output, right? Means when one Baud clock signal is generated, then your pulse pending will be reduced by 1, right? Like when you give in this start pulse, then this pulse pending will be 10 because the data width is 10, right? Now when your first pulse is generated, then this pulse pending will be 9. And then when your second pulse is generated, then this pulse pending will be 8. And that will happen until 10 pulses are generated at the output. Means at the output of Baud clock port, right? So simply write it. If start equals to 1, then your pulse pending signal will match with the data width. Else if when your Baud clock pulse is generated, means when your Baud clock is generated, means this Baud clock is equals to 1, then what will happen? This pulse pending will be pulse pending minus 1. So pulse pending minus 1. Okay. And now and if. So what we have defined in this process block, we are saying that when this start pulse is given, then your pulse pending signal will be matched with the data width. For example, if your data width is 10, then your pulse pending will be 10 as well. When you give this start pulse, right? And when this Baud clock pulse is generated, then what will happen? Then your pulse pending will be pulse pending minus 1. But still, we are generating these Baud clock pulses in an infinite loop. And we do not want this. We want to generate a very fixed number of Baud clock pulses when this start pulse is given, right? So we will write another logic here. And the logic is simply within this if condition. So what I will do that I will run these statements inside another if condition. So write it. So first move it little. So tab. Now give another condition that if this pulse pending signal is greater than 0, then only this Baud clock signals will be generated. And when this is not happening, means when pulse pending is 0, then let's move it here. So when this pulse pending is 0, then what will happen? This Baud clock will be 0 and this bit period counter will also 0, right? Now and if. So now this process will only generate a fixed number of process and that will depend on your data bit. And this second process will tell that when these Baud clock pulses will be generated for your Baud clock generator. One more thing that we have not given the reset condition here. So we will give it as well. So what we'll have when this reset signal is asserted. So if reset is equals to 1, then what will happen? This pulse pending will be 0. Okay. So this is the only statement that we want in this process block for the reset condition. So this process block is also looks good now. Now, if you remember that we have one extra signal that is ready, and this is a output put, and we need to define the functioning for this ready signal as well. And for this, we will write one another process block. Okay. And again, this will be a registered process block. So first give it some name. For example, this is ready output signal, output process, and this is a process with clock and reset in the sensitivity list, then begin, and in the last end process. Okay. Now because this is a register process block, so we will write the basic template for it. So this is if reset is equals to 1, then do something, else if at rising edge of clock, then do something, and in the last and if. Okay. So first we will give the reset condition. So when reset is equals to 1, then our ready output will be 0. Okay. So this ready gets the value of 0. Now at the rising edge of clock, so first understand that what this ready signal will do. So it will tell your UART transmitter that when it is ready to transmit any data, right? This means that when your Baud clock pulses are generating, at that time your UART transmitter is not ready to get any new data, right? Means this ready signal will be logical low. And when all the bits are transmitted and your Baud clock generator is not generating any new pulses, this means your UART transmitter is ready to take the new data. So that's what this ready signal is doing. So basically, this is the indicator that when your UART transmitter is ready to capture any new data. So this is very simple that if start is equals to 1, means when you give the start pulse to your UART transmitter, then your UART transmitter will be busy in transmitting those data signals, right? So if start equals to 1, then this ready output will be 0. Means now it is not ready to capture any data at this point of time. Else if, now we will write the condition that when this ready output will be logical high, means your UART transmitter is ready to capture new data. So I will say that when this pulse pending is equals to 0, means all the pulses are generated, then ready output will be high. Okay. Now and if. So this process is very simple. When reset is applied, then the ready signal will be 0. Else, when you give the start pulse, then your ready signal will be 0 or logical low. Means your UART transmitter is busy in transmitting the data. And when all the bits are transmitted and your UART transmitter is ready to capture any new data, at that time your ready will be 1. Okay. So our architecture part is also completed. Now let's zoom out little, and it's the time when we need to declare all the signals and constant which we have used in this architecture section. Okay. So let's define them. So we will declare all the signals and constant in this section of architecture. Okay. But before this signals or constant declaration, let's define our generic that we have used in this process block here, and that is data width, right? Which is defining our number of data bits, right? As I said, we will define this as a generic. So let's copy this data width, copy, and let's define a generic for this data width. So we define the generics here in this section of entity. So write generic. Now define all the generics in this section here. So we have this data width, and that is integer. And for example, we are giving some initial value of 10. Okay, now we will define this bit period. So this is a constant. So we'll define it here. So this is a constant bit period. that is integer type, I want to initiate this bit period integer with some initial value, right? So this will be like 434. So constant bit period, that is integer type, and it is having the value of 434. Now the question is that how we will define the upper range for this integer. Now for this design, it depends on two factors. Number one is your system clock frequency, and number two is your baud rate. For example, your system clock frequency is 50 megahertz and you are designing the system for a baud rate of 115200. So this upper range will be 50 megahertz or 50 millions, 50, 1, 2, 3, 4, 5, 6, 50 million divided by 115200. So this is our baud rate, right? And the value will be 434. So this constant bit period is an integer type and having the range of 434, right? But instead hard coding this with 434 because now this is very limited to a 50 megahertz system clock frequency and 115200 baud rate. So to make it flexible, what I will do that I will use that same mathematical calculation here. Okay. So what I will do that I will create two more generics. One is system clock frequency. So sys clock frequency, and second is baud rate. And this constant bit period will be system clock frequency divided by baud rate. And now we will define this system clock frequency and baud rate in the generic section. So go to the generic section once again and define these two generics. So this is system clock frequency, that is again integer type, and give it some value. So for example, in our case that is 50 megahertz. So this is 50 million times. And next generic is baud rate. So this is baud rate integer type and the value is 115200. Okay. This means that now you can use this VHDL program for any system clock frequency and any baud rate and for any data width, right? So this is the benefit of using generics in your VHDL programs. So let's come back to the declaration section or declaration part. So I have defined the constant bit period. Now we will define all the signals which I have used in our VHDL program. So first signal is this bit period counter. So bit period counter. Now this is integer type. Now this is fine if you declare your bit period as an integer like this. But as I said in the best practices session, that you should always define a range with your integer values. And that will help to optimize your FPGA resources. And we will also define the range for this signal. So range from 0 to, so if you notice in this process block here that it is counting from 0 to bit period, means because when this bit period is occurring, we reset the bit period counter to 0. This means that it will only count from 0 to this bit period range. Okay, so define it signal bit period counter integer range 0 to bit period. Okay. Okay, so we have defined this bit period counter here. And let's look for any other signal which we have used. Yeah, so we have used this pulse banding. So we will define this as well. So this is a signal pulse banding. And this is integer type and having the range from 0 to, now if you look at this process block of for this pulse banding, then you will see that this pulse banding having the highest value of data width. And for each Baud clock pulses, it is reducing its value by one factor. So this signal pulse banding will be having the range from 0 to this data width. Okay, so this is having the range from 0 to data width, right? Now let's see if any other signal is pending. So this Baud clock, so this is output. So we have already defined that in the entity section. This bit period counter, we have defined that as a signal. Then Baud clock, again, this is the output port. Period counter, we have defined this. Now pulse pending, we have already defined this again. So everything has been defined. Now this ready. So this is our output port. So we have already declared this in the entity part. And now all the signals are defined for this project. Okay, so this is our VHDL code. Now let's zoom out little so we can see the whole program. Okay, so everything is looking good. Now let's save this program. Now this time I will compile this program in the model sim simulator. So for this I will open this model sim. Okay, so open this model sim simulator or model sim tool. Okay, let's maximize this. Now first we will create a new project. So I will go to this file tab and now click on new. Now you will see this project section here. So click on this. Yes. Now give some project name. Suppose our project name is UART. Now give the project location. Now suppose I want to save this project in this folder. So I have already created this UART project here. And let's create a new folder here. So click on new folder and give it some name. So this is model sim UART project. Okay. And select this folder. So this will save at this folder location and the project name is UART. Now click on OK. Now it is asking if you want to create a new file or you want to add any existing file. So I will select this add existing file because we have written our VHDL code in Notepad and saved it. So I will browse that file and I will open it. So we have this Baud Clock Generator, that is VHDL file that we have just written. So I will select this and click on open button. Now click on OK. Now if you have more files to add, you can again click on this add existing file and follow the same process. And once you add all the files, then you can click on this close button. So now you can see that this Baud Clock Generator.vst, this file is listed here. Okay. Now this question mark and the status is because we have not compiled this yet. We have only added this file into this project. So first we will compile this VHDL program for any syntax error. Okay. So you can see this compilation button here. So you can click on it and the compilation will start for this program. Else you can simply select this file, then right click and you will see this compile button here and just click on compile select. Okay. Now if you have multiple files in the same project, then you can select this compile all option here. But we have this single file at the moment. So I will select it and then click on compile selected. Okay. Okay. So you can see the compilation has given us some error. Now I will click on this. So it will tell that what is the problem. Okay. Now I will double click on it. So it will land me on the problem. So it is saying that there is some problem at this line here. Yeah, that's right. Because when you define the last generic in this section, then the semicolon at the end after closing the bracket. So this follows the same syntax as the port declaration, right? So I will save it again. Let's save it and then right click, compile and compile selected. Okay, now this more error. Now let's see what it is saying. Okay, double click on it. Okay. So this Baud clock, that is an output and this is STD logic data type, right? So I have to use single quotes to write any value for STD logic. Now save this. Let's compile it again. Compile, select it. Okay. So number of errors are reduced now. Okay. Now what it is saying. So it is saying that at line 60, I have used this Baud clock to check for any condition. Means we have used this Baud clock signal to read data from it. But this Baud signal is actually an output signal. And this error has come because VHDL does not support this. This means that you cannot read any signal in your VHDL program which is declared as an output port. And here we have declared this Baud clock as an output. So that was not allowed in the previous version of VHDL compilers. But if you are using the recent VHDL compiler, then it is supported. So you can see that it is also listed that this is the error. that you are using this Baud clock as an output port, but at the same time, you are reading this output signal. And this is not allowed in the previous VHDL compilers, but that is supported by VHDL 2008. Okay, so I will close this. So I will update the VHDL compiler for this project. So for this, I will select this file. Now click on properties, and here I will select this VHDL and select this 2008 version, and that's it. Click on OK. Now again, we will compile it again. So compile selected, and you can see that error has been gone. So this is compile of Baud Clock Generator was successful. So this means that our Baud Clock Generator is successfully compiled and it is free from any syntax error. But that does not mean that this program is logically correct, right? So to test the functionality of our program, we will simulate this module in the waveform. And for that, we will write a test bench in a next section. And then we will simulate our program in the terms of waveforms. And we will see that if this program is working fine logically or not. So that is one module of our UART transmitter. And before using this module in the UART transmitter, we will test this module. So in the next session, we will write a test bench for this module in VHDL. And then we will see the simulation results as well. In the last session, we have written the VHDL code for Baud Clock Generator. And we have also fixed all the syntax error. Now this is the time to test it functionally. And for that, we will write a test bench in VHDL. So as I explained, test benches is kind of a separate VHDL code, or you can say a separate VHDL module without any input-output ports in your design. Instead, it uses signals to declare the necessary connection for your test module. We will see this in our VHDL code in some time. So let me give a quick brief and then we will write the VHDL code for this. This is our Baud Clock Generator. We have this start signal as an input and we have two outputs, Baud clock and ready. Now we give a pulse at the start input and then this module will generate 10 pulses at Baud clock output. And these pulses must follow the baud rate of 115200. Means the timing difference between two successive pulses must be 8.7 microseconds, right? And after 10 pulses, Baud clock output should be in ideal state. Now, ready output will be high when this module is not generating any pulses. Means this module is ready for capturing any new input. And once we give the start pulse, then this module will be busy in generating 10 pulses. And for that time, this ready output will be logical low. And once all the pulses are generated at the Baud clock output, then again it will go to the logical high. Means it is ready again for the next data transmission. So to test it, we will follow our project specification. Means our operating frequency will be 50 megahertz. Means one clock cycle will complete in 20 nanoseconds. Our baud rate will be 115200. Means the time gap between the two successive pulses must be 8.7 microsecond. And we will generate 10 pulses at the output. So we will start from the reset condition and reset will be applied for the first 100 nanosecond. Then after 100 nanosecond, reset will be deasserted. And then we will give the start pulse for one clock cycle. And then everything must be handled by our test module, like generating 10 pulses at the baud rate of 115200 and ready signal management, etc. So this is our simple test sequence. Okay, so in the last session, we have designed this Baud Clock Generator and we have written this VHDL code for this Baud Clock Generator design, right? And we compiled it into the model sim simulator and we fixed all the syntax error in this program. But that does not mean that functionally this program is correct, right? So in this session, we are going to test this Baud Clock Generator functionally, that either this program is working correctly or not. and we are getting the expected results or not. So we will test this Baud clock generator with data width of 10 with 50 megahertz of clock frequency and the baud rate of 115200. So first we will open the model sim simulator and then create a project for this Baud clock generator and for the test bench for this Baud clock generator. So open the model sim simulator. So model sim, click on this. Now model sim is opening. Let's maximize this window. Now, once again, we are repeating the steps in this program as well. So what we will do that we will create a new project for this Baud clock generator, which we have already written in the last session. So we will create a project and then import that Baud clock generator files in this project. So for this, we will go to this file tab. Now click on this new button and then you will see this project option here. So click on this project. Now just a small warning that this operation will close the current project. So continue. Yes. Now I will give a project name for this project. Suppose this project is Baud clock generator. So this is Baud clock generator. Now give the project location that where you want to save this project. So click on browse. Suppose I want to save this on this C drive and this 0 model sim projects. And I have already created the folder that is UART project. So I will select this. And now I have the another folder that is Baud clock generator. So I will open it. Now, as I told you that all of my VHDL files are placed at one single folder and that is named as source. So I will create a new folder here and I will give it a name that's source, SRC. Enter. So this is the folder for our all of the VHDL files. Now I will create another folder for this model sim project and suppose this is named as model sim. And now I will create one another folder for the test bench. So create a new folder here and give it a name test bench. Okay, so select this model sim folder and we will save our Baud clock generator project at this location. Okay, now select this and click on this select folder. Now if you see this default library name, so this is our work library and leave this as it is. And now click on OK. Now here you have four options. So first is you can create a new file. So you can create a new VHDL file here, or you can add an existing file, which we are going to use here because we have already written the VHDL code for Baud clock generator and we are going to import that file. So click on this add existing file. Now we will browse the location. So go to this Baud clock generator folder. And as I said that all of my VHDL files are present at this source file or source folder. So I will copy that VHDL file to this source folder. So copy this Baud clock generator file. I have already copied this file at this location. So I will just open this source folder and paste it. Now click on open and then click on OK. Now click on close. Now you can see this Baud clock generator.vsd file is listed here in this project. And you are seeing the status that is question mark because we have not compiled this program yet. So first we will compile this Baud clock generator.vsd file. So for this, just right click on this file. Now you will see this compile option. So select this. Now you have multiple options here. But because we have just one single file listed here, so I will click on this compile selected. So let's compile it. So you can see that it has returned one error here. So you can see it here. Let me make this window a little big so you can see it. Now, if you double click here, so it will tell you that what is this error. Let me make it little wide first. So model sim is complaining that I have used this Baud clock as an output, but at the same time, I'm reading this output port that is Baud clock, and that is not allowed by the VHDL compiler. But the recent version of VHDL compiler actually allows this. So it is also mentioned here that is VHDL 2008 allows reading outputs. And we have seen this error in the last session as well. And the fix is really simple. What we will do that we will select this VHDL file or we will select this VHDL project. Now right click and go to the properties. Now you will see this window here, and we will go to this VHDL tab, and you can see that it is by default selected 1076.2002, but we will select this 2008 version. So just simply select this and then click on OK. Now we need to recompile our program first. So again, select this VHDL file, right click, now select compile, and then click on compile selected. So you can see that that error has been gone, and we have this success message, that is compile of Baud Clock Generator.vsd was successful, and you can see the right tick here as well. Now it's the time to write a test bench for this project so that we can see the outputs in the form of waveform windows, and we can verify that this program is functionally correct or not, right? So we will write that program in the Notepad++ once again. So select this. Now first I will create a new file. So click here. And the first step is to save this file as an .vsd file. And that is really important, because when you tell Notepad++ that you are writing a VHDL code but not a plain text, so it can highlight the keywords and other necessary things for you. So first save this file. So go to this file tab and click on save as. Now we will save this test bench file in the Baud Clock Generator project, and we have created a separate folder for this at the starting of our project. So we have this test bench folder here. So simply select this and open it. Now give the name to this file. So suppose this file name is Baud Clock Generator _tb for test bench. Now this is important step, that you need to select the right extension for save as type. So this file is .vsd. So we need to select basic file. So you will see it here, that is basic hardware description language file. So select this and now click on save. Now I am not writing everything manually. So what I will do, that I will go to this Baud Clock Generator project or this Baud Clock Generator.vsd file where we have written the program for this Baud Clock Generator, and then I will copy this part, that is library declaration and entity declaration of our Baud Clock Generator file. So I will copy this and now come back to this test bench file and paste it here. So this is our library declaration. Now I will make another copy of this entity. So copy this once again and paste it here. Now the entity name is Baud Clock Generator _tb for test bench. And now because this is the test bench, so we do not need any generic and port to be listed here. So I will simply remove these tags, that is generic and port declaration, from here. So this is entity Baud Clock Generator _tb is and Baud Clock Generator _tb. So this is our entity declaration for Baud Clock Generator test bench. So we have written this library declaration and we have written this entity declaration. Now the next part is architecture section. So write it, architecture behave of this Baud Clock Generator _tb is. Now leave this as it is here. Now type begin and in the last write and architecture. So and behave. So this is our architecture body and we have two sections here. So this section is declaration part or declaration section, and this section is our functional section. Now because this is the test bench, so we need to use that Baud Clock Generator file or that Baud Clock Generator module as a component here, right? And for that, we need to declare that program as a component here in this test bench program. So I have already copied it here. We just need to replace this entity keyword with the component. So this is the keyword again. And in the last, this Baud Clock Generator, replace this with component. So we have declared this component part here. And this means that this Baud Clock Generator, so that was our main module in the last session, and that module is working as a small component of this test bench that is named as Baud Clock Generator _tb. Now at the same time, I will also declare the signals for this test bench. And we know we have these 5 signals here. So I will copy this and now paste this here. And now I will add signal in the starting of these ports. So now this is a signal that is named as clock. Now signal don't have any direction. So this is removed. So same signal reset, signal reset, signal start. Now copy this, paste here and paste it here. So I have declared all the signals for this test bench as well. So this completes our declaration section. So first we have declared this component, and for this we simply copied the entity of this Baud Clock Generator and pasted it here and replaced the keyword entity with the component keyword. And then I have declared all the signals for this test bench. And these are simply the input output ports of your main module. Now there is a small syntax error because we have not written the semicolon here. So just use it. And now quickly align all of the signals so that we can read it easily. So now this looks good, right? Also, we need to remove these initial values from here. So I will just remove them. And now this looks good. Okay, so now the main part is coming, and that is writing the test bench for this Baud Clock Generator module. And we will write this in this functional section here, and that is after this begin keyword. So first I will drive this clock signal. Now before we drive the input signals for this Baud Clock Generator module, let's instantiate our component first. So what I will do that I will copy this text from here. So I will copy it and then I will paste it here in this section here. Now first give this component some name. Suppose I am giving this DUT or device under test. You can give any other name as well, like UUT means unit under test or something else. Now remove this is from the last. Next line is generic map. So write it generic map. Now I have to give the data width for this module. Suppose I have total 10 number of bits that need to be transferred over the UART communication or RS-232 protocol. Means one is start bit, 8-bit data lines and one stop bit. So total 10 pulses I needed. So our data width will be 10. Now replace this semicolon with the comma. Now our system clock frequency. And as I said that we are working on 50 megahertz of clock frequency. And that is our FPGA board frequency, right? So our system clock frequency will be 50 megahertz, means 000. Now comma and replace this semicolon. And now we will give this baud rate. And now suppose we are transmitting our bits at the baud rate of 115200. So our baud rate is 115200. And now bracket closed and remove this semicolon from here because this is one single statement and that will continue with the port declaration or port mapping as well. So the next line will be port map. So this is port map. So this is the time that we will tell that what port of this Baud Clock Generator will connect to which signal of this test bench. So generally I give the same name as the input output ports of the main module. So clock is connected to clock, comma, reset is connected to reset, comma, start is connected to start signal, comma, now baud clock is connected to baud clock, comma, and ready is connected to ready. And then bracket closed and semicolon. Now don't be confused with these names here. This name here that can be anything. So you can say that this clock is connected to this clock ABC or some signal like ABC or DEF or any random signal name. But it is always better that you map your input output ports of the main module with the similar kind of signal name. And that will ease your understanding when you are debugging your program or you are checking it sometime later in the future. So always try to give the same name as the ports in your top module or the port names of your test module. So clock is connected to clock. But there is one important thing to note here, that you can give any name like here to this signal name like ABC, but you cannot mention this clock signal here with any random name. So it must be clock here. Why? Because we have defined this Baud clock generator as a component here, and that is clearly mentioning that this clock is an input port, this reset is an input port, this start is an input port, Baud clock is an output port, and ready is an output port. And these port names are exactly same of your Baud clock generator module. So if you see this entity declaration here, so these names are exactly same. So this is clock, reset, start, Baud clock, and ready. So we cannot change these names here in this component section. I have to use the same names here in this component declaration as well. And so that must be same here, like this clock, this reset, this start, this Baud clock, or this ready port. Okay, so remember this. This name can be anything. So this is clock is connected to clock, but this must be same as in component declaration or your DUT module ports. Okay, so that is the code for our component instantiation. Now the main part of Testbench, and that is driving the input ports of the main module, that is Baud clock generator in our case. So let's quickly see that what we need to drive in this program here of this Testbench. So we have this clock, so that is input. So we need to drive this. Then this reset, so that is input. So we need to drive this as well. We have another input, that is start. So we need to drive this as well. And we have two signals, and that is output type. So that is Baud clock and ready. So you can see this ready is this output port, and this Baud clock is an output port. And all other three signals or all other three ports are input type. So we only drive the input ports in the test bench, and we see the results of the output ports in the form of waveforms, so that we can verify that we are getting the expected results or not. But before going further, I can see there is a syntax error. So I will just correct it simply. So these are the signals. So there is no input output ports. I have just copied these text from the port section of component. So that was copied. So now this looks good. So first we will drive this clock signal. And to drive this clock signal, I will simply write one simple statement. And that is clock gets the value of not of clock after 10 nanoseconds. Now, why 10 nanoseconds? Because our system frequency is 50 megahertz, means one cycle period is 20 nanoseconds. And that means I need to toggle this clock signal at every 10 nanoseconds. Means for 10 nanoseconds, its value will be 0. And for another 10 nanoseconds, its value will be 1. So one complete cycle will be 20 nanoseconds. Now there is one important thing, that when you are using this statement, that is clock gets a value of not of clock after 10 nanoseconds, I need to initialize this clock signal. So I will initialize this with colon equals to 0. Okay. Now what will happen if you don't initialize this clock signal with some value? So if you do not initialize this clock signal, then its value will be uninitialized, or the value is undefined value. And here you are saying that clock gets the value of not of clock. So the question is that what will be the value of an uninitialized value or undefined value? And that is undefined, right? So we need to define some defined value at the initial stage. And that is why I have initialized this clock signal with some initial value of 0. And now this code will work fine. Even though there is one another way of generating this clock signal, and that is by using the process block. So let me quickly show you that as well. So I will write a new process. Suppose the name of the process is clock generator or clock gen. Now this is a process. Now begin and end process. So this is our process body. Now clock is having the value of 0. Now wait for 10 nanoseconds. Now clock gets the value of 1. Now wait for another 10 nanoseconds, and that's it. And now if you're using this process block to generate your clock signal, then you do not need to initialize this value here. You can simply write that signal clock colon std logic semicolon. Why? Because when this process will execute, then first clock will get the value of 0, then it will wait for 10 nanosecond, and then the value of clock will be 1, and then it will wait again for another 10 nanosecond. And that will happen in the loop. So when this process will execute for the first time, it will encounter this statement, that is clock gets the value of 0. Now there is one important thing, that do not try to write like this, that is clock gets the value of 0 and then clock gets the value of 1. Now you may say that this is executing sequentially. So first clock will get the value of 0 and then clock will get the value of 1. But that is not true. Because if you remember from our previous session, then I explained you that if you are writing two statements like this, then these two statements executes at the same time. Although they are sequential execution, but signal assignments happens at the last. So this first statement, that is clock gets the value of 0, will be completely ignored and you will get the clock value of 1. Okay. Okay, so let's correct this. So remove this line here. Now another important thing is that this line and these multiple lines are doing the same thing. Means either you can use this line or this set of statements, but you cannot use both of these statements. Okay, so I will remove these multiple lines from here and I will use this one single statement in this test bench here. And for this we need to initialize our clock signal. So let's initialize it with 0. Okay. Okay, so what we did, that we have defined this clock signal, or you can say that we have derived this clock signal with 50 megahertz of clock frequency. And now we have two more inputs to drive, and that is reset input and start input. And we do not need to do anything for this baud clock and ready port because these are the output ports. Okay, so let's create one another process for these two inputs, that is reset and start. So let's write it here. You can write it anywhere, like after this begin keyword or after this clock assignments or even after this DUT. It really doesn't matter that where you are writing your process block, because all of these statements are separate with each other and they execute separately as well. So let's write the process here. So first give it some name. Suppose this is a main process. Now we will go a little up so that we can clearly see. Okay, so main process colon process, now begin and end process. Okay, so this is our process body. Now if you notice, then this process block does not have any sensitivity list here, and that I have did intentionally. Why? Because we are going to use wait statement in this process block. So these are some special kind of process blocks where you do not write any sensitivity list. But the most important thing to note is that you cannot synthesize these type of programs. But that is completely fine because we are writing this test bench to simulate our VHDL module, like in case that is Baud Clock Generator. And we are not going to implement this test bench into the FPGA board. So we really don't care if this code is not synthesizable. Okay, so let's start our process. So begin. Now at the starting of my simulation, I want to assert reset signal. And then after some time, I will remove the reset from the module so that our module can function after the reset. Means at the very initial stage of simulation, our reset signal should be high. So reset is 1. Now I will wait for some time. For example, let's say that this reset condition is asserted for 100 nanosecond. So reset gets the value of 1. Now wait for 100 nanosecond. Now you do not need to wait for that long period. So you can short it as well, like 50 nanosecond and so. But let's say for our code, this is 100 nanosecond. And what will happen after this 100 nanosecond, that our reset signal will goes to low. Means after 100 nanoseconds, our Baud clock generator is come out from the reset condition, right? So this is one input, that is reset. But what about the another input, that is start? So let's define that signal here itself. So at the very starting means when reset is equals to 1, I will say that our start signal is 0, right? So start is 0 because when our module is in reset condition, then I do not want to send anything. So start is 0. But it is completely fine when you test this module when reset is equals to 1 and start is also 1. And even I will say you should test these conditions as well so that you come to know that what will happen in this situation, that when reset is high and start is also high. But in this test bench, let's ignore this condition. So first, my reset signal is asserted at 0 timestamp, and at the same time, my start signal is 0. Now I will wait for 100 nanosecond, means after waiting this 100 nanosecond of time period, our reset signal will goes to low, means our module come out from the reset condition. And now I also want to drive this start input. But instead writing it straight after the 100 nanosecond, I will prefer to wait for the next rising edge. So what I will do that I will write the condition that wait until rising edge of clock. Okay. Then what will happen? Then this start signal will go to high and then wait for another rising edge of clock signal. So wait until rising edge of clock, and then what will happen? This start signal will go to low. Now that's complete our driving the signal reset and signal start. Now this is the most important step of the test bench, that when you are driving your input ports of any module in the test bench, then at the last of process, the entire process block for re-executing, means I have to stop this process block here after this start gets the value of 0 statement. So I will use this wait keyword. So this is most important to add this statement here. If you do not write this wait statement here, then what will happen that at the 0 timestamp, your reset signal will be high, your start signal will be 0, then your simulator will wait for 100 nanosecond at this line, and then your reset signal will go to 0, then your simulator will wait for the next rising edge of your clock signal, and at that time your start signal will go to high, and then it will wait for the another rising edge of clock signal, and then start will 0. But as soon as this statement hits, and if you're not using this wait statement here, then your process will jump to this statement here, and the whole process will continue to run once again. So always remember that you need to hold your process execution once you drive all the input signals in your process block. Okay, so always remember this. Another important thing, and that is sensitivity list here. So you must notice that we have not written any signals or any port in the sensitivity list of this process block because we are using wait statement in this process here. So we do not need to write any sensitivity list here. If you write them, then you will get the syntax error while you are compiling your program. Okay. Now, if you wonder that why we have not written this statement, that is start gets the value of 1 here, and why we have waited for another rising edge of clock. And that is because we wanted to synchronize this start signal with the system clock frequency. So we have used this wait until statement here. If you do not wait for the rising edge of clock, then your module can have timing issues because your flip-flop needs some setup time to capture the input and to pass it to the output. So as a safe side, after this reset condition, we will wait for the rising edge of clock signal. Then start will get the value of 1, and after the very next pulse of the rising edge, your start signal will be 0. Okay, so that's complete our VHDL test bench code, and everything looks good to me. So now it's the time to compile this test bench program, and then we will see the results in the waveforms. So let's move to the model sim simulator once again. Now I will right click here. Then you will see the option of add to project. And now you will see the same options here. That is new VHDL file, add an existing file, simulation configuration and folder. So I have written the test bench module in the Notepad++ editor, right? And here we are just importing that file. So I will choose this existing file option. So click here. Now click on browse. So Baud Clock Generator is our main folder, and here we have this Testbench file where we have saved our file, right? So we have this Baud Clock Generator _tb.vsd file. So select this and click on open. So this is the top module. Now leave everything default here, then simply click on OK button. So you can see that this Baud Clock Generator _tb.vsd file is listed here in this project, and the status is question mark because we have not compiled it yet. So first we will compile it. So select this file, then right click and then click on compile and click on this compile selected. Okay, so model sim is saying that there is some error, so just click on it. Now why did little? Okay, seems like I have not saved the test bench file. So I will go to the Notepad++ once again and save that file. So save. Now come back to the model sim simulator. Okay, so now the status is crossed. So I will recompile it once again. So right click, compile and compile selected. Okay, so we have few errors. Okay, so there are few things that model sim is complaining about. So let's see. So that is saying that at line number 49 and 52, it is expecting semicolon. So go back to our VHDL program and look at this 49 and 52 line. So this 49 and 52 line. And it's right because we have not used semicolon at the end of these statements. So let's save this file once again and go to the model sim simulator, close this and right click, compile, compile selected. So you can see that the compilation is complete and it is successful. Okay, so you can see that we have two files that is inside the project tab. And now we will switch to this library tab. Now there are many libraries are listed here. You can simply ignore them at the moment, but what is important for us, that is work library, where we have defined our Baud Clock Generator and Baud Clock Generator Testbench, right? So we will focus on this work library only. So what I will do, that I will expand this first, sort it by name. So I will see this work library at top. So this is our Baud Clock Generator Testbench, and we have behave as an architecture, and this is our Baud Clock Generator main module, right? So we are going to simulate this Testbench program. So I will select this, then right click and then click on simulate. Okay, so it is giving some error in the loading and it come up with some error. Okay, so it is saying that there is some problem at this line number 73. So let's move to our VHDL code. So this 73 line is actually our port mapping of component instantiation. So these all set of lines are actually one single statement. So it is saying that there is some problem in this component instantiation. So let's move to the model sim once again and see that what it is saying. So it is saying that no default binding for component instantiate UUT. So these are system clock frequency and theta weight. So let's jump to the Baud Clock Generator VHDL code. Okay, so let's remove the initial values from here. Let's remove them. And let's see if these changes are solving the problem. So let's save this file and save this file as well. Now go to the model sim simulator and go to this project tab. Now we will compile both of these files here. So compile, compile all. So both of these files are compiled successfully. And now go to this library tab and select this Baud Clock Generator _tb. Right click and then simulate. Okay, so let's try to open this Baud Clock Generator file from here. So double click on it and let's see what is happening here. Oh, seems like some another file that has been copied at the same location. So what I will do, that I will copy our current VHDL code from here and then I will paste it at this program. So I will save it now and then I will right click and then compile all. Okay, so now the compilation is done and there is no syntax in our VHDL code. So let's jump to the library tab once again, and now select this Baud Clock Generator underscore TB and then right click simulate. So you can see that if everything is going well, then you will see this simulator window here. Now, if you focus on this main window here, then you will see multiple tab here, right? So what I will do that I will switch to this waveform tab. Now you can see that everything is blank here because we have not added any signals here. So you can see that is object window here, and this is your files and library view. So you can see that this Baud Clock Generator underscore TB, that is our top level module, and you will see the plus button here. So you can expand it from here. So you will see that under this Baud Clock Generator test bench, you have this DUT or device under test, and that DUT having three processes, that is bit period process, pulse control process, and ready output process, right? So if you select this DUT, then all the signals are listed here in this object section. And I can select the important signals and input output ports from this list, and then I can move them to this waveform window. So what is important? So clock signal is important, reset signal is important, start is important because these are input output ports, system clock frequency, that is important, and ready port is important. So these five objects are our input output ports of DUT or device under test. So you can simply right click and you can click on add waveform, or you can just simply select them and just drag and drop to this waveform window. Now just make this window little wide so that we can see all the signals listed here. I will also add few more signals in this list. So I will select this bit period counter and this pulse banding signal. So these are our internal signals of DUT, right? So move these two signals to this waveform window. Now let's quickly adjust these windows so that we can have better picture of these waveforms. Okay, so this view is better. Now you can see that there is nothing mentioned in this waveform window here because we have not compiled our project yet. So what I will do now, that I will run my simulator for some specific time. So for that you have couple of options. So you can see that there are multiple buttons are listed here. So you can simply click on these buttons, like this is for restarting your compiler. This is run your simulator for some specific time, and that is mentioned here. So when you click on this button, then your simulator will run for this 100 picosecond. You can change this time as well. For example, 100 nanosecond. So you can change it to 100 nanosecond. And there are few more options like continuous run, break, like that. And we have one another method, and that is by using the transcript. So I will go down to this list. I can give the command to my simulator like that. So I want my simulator to run for 200 nanosecond first. So I will write run for 200 nanosecond. So you can see that my simulator is simulated for 200 nanoseconds. Now click on this window here and then zoom out little and see what is happening. So this is our clock input that is having 50 megahertz of clock frequency. So first verify that the clock signal is actually 50 megahertz or not. So how we will do this? So let's zoom a little so that we can see one clock cycle complete, and let's move our cursor at this point. Okay. So what I will do that I will add one additional cursor to this waveform, and then I can see the timing difference between two timestamps. So for that, I will just click on here. So this is the button for insert cursor. So just click on it and then move this to this one clock cycle. So for more precise results, let's zoom a little more. So let's see the timing between one clock cycle. So this is our starting point and this is our one complete cycle. Okay, so let's see how you can measure this. So this slider is at this timestamp and this slider is at this timestamp, and this white text is actually the difference between these two sliders. So if you notice, so this is 19871, means nearly 20 nanoseconds. There is little variation because these sliders are not exactly at this point. So let's move this cursor here. So you can see that we are starting from here. So move it here and let's adjust it here. So you will see that is 20 nanosecond. So our clock period is 20 nanosecond, means our clock frequency is 50 megahertz, right? So the clock generation is perfectly fine. So let's zoom out little and let's remove the extra marker. So just click on this minus button. Now we will focus on this reset input. Okay, so let's see that what is happening. So this is our reset waveform. Okay, so we have said that for 100 nanosecond, our reset signal is asserted. Means reset signal value is 1, and then after 100 nanosecond, our device will come out from the reset condition, right? So let's see if this is happening or not. So this is our 0 timestamp. And if you will notice, then reset signal is triggered to 0 here. So let's move this cursor to this point and you will see that is 100 nanosecond. Means after 100 nanosecond, our reset signal is deasserted. Then after reset, we set our start signal and that is after 1 rising edge. So you can see that this is the point where reset is logical low and then it is waiting this signal that is start. Let's move this up. So this signal is start is going to high after 1 rising edge. So this is the timestamp when reset signal is deasserted and then the next rising edge is this point. Okay. So you can see that at this point, our start signal is high for 1 clock cycle. And for the very next rising edge, our start signal goes to low. So that is also working fine. So this is good, but we have missed to add Baud clock to this waveform. So what I will do that I will select this Baud clock, which is our output signal, and that is our main signal as well. So I will move this signal to this list here. And now I need to restart my simulation. So I will just quickly click on this button. Now click on OK and then give the same command that is run for 200 nanosecond. And we get the same results here. So we have already verified this clock signal. We have verified our start signal and reset signal, right? And now we are going to test this Baud clock, which is our main output. So what it will do that it will generate 10 number of pulses at the baud rate of 115200. So that what we are expecting from this Baud clock output. So for that, we need to run the simulator for a little longer time. So let's say we are running this for 200 microsecond. So give the command run for 200 microsecond. Now this is a little longer duration. So I will zoom out this waveform window. So let's see what is happening. Okay, so you can see that this section after this point, nothing major is happening. So these are flat lines here. But what is important that is before this point. So let's zoom in little and let's slide this window. And now let's see that what is happening. Well, to brief this, let me add one more signal to this list and that is pulse pending. So let's move this as well. Okay, so let's move to this initial point first and let's zoom in. Let's move this cursor. I think this is a good size and let's move to this point here. So I have explained this, right? So this is our clock signal. This is our reset signal that is deasserted at this point. And then after the next rising edge, we have this start signal. So that is high at this point and that goes low at this point. So when this start signal is asserted, we moved value 10 to this pulse pending. Means our system has to generate 10 pulses to transmit 10 number of bits, right? And at the same time, this ready output goes low. So you can see that at this point, when we start generating pulses for our UART transmitter, this ready signal goes low. Means now our UART transmitter is not ready to capture any new input because it is busy in the transmission of data, right? So let's see if it is generating 10 pulses or not. So let's zoom out little. So this is our first pulse. This is our second pulse. This is third pulse. This is fourth. This is fifth. This is sixth, seventh, eighth, ninth, and 10th. Means our program is working well. Because when we are giving the start signal, then it is generating 10 pulses for us. And you can see that it is showing the pulse pending. So at this time, we have 10 pulse pending. When one pulse is generated, then we have 9 pulses remaining. And then when second pulse is generated, then we have 6 pulses remaining. And when all the pulses are generated, then we have 0 pulses remaining. And now when all the bits are transmitted, and that means our transmitter is now ready to capture any new input. Means this ready output goes to high. So you can see that once all the pulses are generated, then our ready signal is set to high. So this is our ready output. Okay. So what we have tested, that we have tested the clock frequency, that is 50 megahertz, means 20 nanosecond is our clock cycle. Next, we have seen the reset condition. So for 100 nanosecond, reset is applied, and after that, reset is taken back. Then next, we have this start signal. So after the reset condition, we have given start pulse at the next rising edge of clock frequency. And after that, we have generated 10 Baud clock pulses here. And once all the 10 pulses are generated, then our ready signal goes to high. This means functionally everything is working fine. But still, there is one more important thing to test here, and that is baud rate. Because we have tested that it is generating 10 pulses, but we have not tested that it is generating at the baud rate of 115200 or not. Right? So how we will test this? So we will capture the timing difference between two pulses. And if it is 8.7 microsecond, then this means that our timing specification is also fine. Now, why this 8.7 microsecond? Because if we use a calculator and we divide this baud rate from 1, so 1 divided by 115200, and we get the result. This is 8.68 microseconds. So let's see if we have the same timing difference between two pulses or not. Okay, so let's minimize this and move to this waveform window once again and see the timing difference between any two pulses. So you can choose these two pulses or these two pulses or these two pulses, anything, because the timing gap between two pulses are same for all these successive pulses, right? So let's zoom in little and let's add a marker to some specific point. So let's add a marker and let's zoom in little more and let's sync it to this point here. And now we will move to the next pulse. Okay, so the next pulse is here. Okay, so let's zoom a little more so that, yeah, so this is perfectly fine. So let's see what is the timing difference between these 2 points. So you can see the timing difference is 870,000 picosecond. And if you convert this to nanosecond and then microsecond, then you will get 8.7 microsecond. So let's check this. So this is nanosecond. So this is 8700 nanosecond and 8.7 microsecond, right? This means our timings are also perfectly fine for this 115200 baud rate. And our system is generating each pulse at the gap of 8.7 microseconds. Now, this is one module of our big project, that is UART communication. And this is just a Baud clock generator, which is a very small part of this big project that is completed now. And we have checked the syntax, so that is correct. We have checked the simulation where we have also validated the timing variations and the functionality of all the input output ports of this Baud clock generator module. Next, we will work on serializer module. So first we will design that serializer and then we will write the test bench for our serializer module. And then after that, next step will be UART transmitter. So we will develop that UART transmitter and then we will test it. Now in this session, we have gone through to the original Baud clock generator program. Then we have explained the test bench module. We have gone through to the multiple errors and then we have fixed them as well. And in the last, we have validated everything from the functionality to the timing variations. And we are pretty satisfied with the results now. So that was our results of Baud clock generator. And I'm pretty satisfied with the results. because our module is working fine as per our expectations. Now, even if you want to test your module for more test sequence, then you can also do that. Like what will happen when the reset is applied, but at the same time, start pulse is also given. What should happen in this scenario? And if your module is working as you are expecting from it, so you can test that. There can be more test combinations as well. So you should also consider them. So we have completed one part of our UART transmitter. Now we will work on the second component, and that is serializer. So in the next session, we will understand the functionality of the serializer first, and then we will code it and test it. In previous sessions, we have developed Baud Clock Generator and tested it as well. Now we are developing the second component of our UART project, which is serializer. So first, we will understand the high-level concept of serializer, like what it will do and how it works, and how we will code it and test it. So look at this simple block diagram first. This module has load input and DIN input. They are marked with the red color. Now, when we assert this load input to our module, then this DIN input will load into the shift register. So question is, why we need shift register? Because this DIN input is a parallel data, but RS-232 protocol uses serial communication. So we have to convert this parallel data into the serial data stream. And then this serial data will be transmitted over the RS-232 protocol one by one in a sequence. So when we assert this load signal, then this DIN data will be captured by this shift register. And now we have to convert this data into a stream of serial data. So to achieve this, we have to shift our capture data one by one. And for that, we will use one another input, and that is shift enable pin. Means when this shift enable pulse is given to our shift register, then our shift register will shift and rotate its data by one position. And we have to rotate our data to the right. Now the question is that why we are rotating data to the right, not left? Because RS-232 protocol transmit the least significant bit first, means LSB first, and then it transmits the MSB in the last. So what we will do that we will transfer the least significant bit of this shift register. And once it's transmitted, then we will replace this LSB with the next transmitting bit. Means we are always transferring the same index, but we will override the content of that index with the next transmitting bit. So we will shift the registered data to the right for each shifting pulse given. And we will repeat this process until all the bits get transmitted over the RS-232 protocol. Now because we are shifting our shift register data to the right, so we have to insert some data at the MSB, right? So we will insert 1 at the MSB of this shift register data. Now the question is that why we are inserting 1 at the MSB, not 0? And the reason is RS-232 protocol standards. Because at the ideal state means when there is no data transmission happening, RS-232 protocol remains at logical high. So until we have the data to transfer, it will send the bits one by one. And once all the bits are transmitted, then this inserted value 1 will reach at the LSB position. Means now our module will be in ideal state. Because when all the data bits gets transmitted, then all of these bits will be replaced by logical 1 as we are inserting this value every time when LSB bit is shifting out. So remember this, we need to insert logical 1 when we are using RS-232 protocol like this. Now we need to understand that our data bits will transmit and our shifting operator will trigger when we give a pulse at this shift enable pin. So this shift enable pin will be derived by the Baud Clock Generator, which we have developed in our last session. So this is the whole process behind this serializer module. Let me quickly brief it. We have these three inputs: load, D in, and shift enable. And we have one output, D out. Input D in is a parallel data, and output D out is a serial data. So we need to convert our parallel input data into a stream of serial data, and that will be achieved by this serializer module. So when this load pulse is given, this D in data will be captured by the shift register. Note that this load signal will be only given for one pulse only. So once the input data is captured by the shift register, this load signal will be deasserted. And once you deassert this load signal, then your input data will not be captured. Means if you change this D in data after it, then the new data will not be considered in the current transmitting sequence. So our transmitter should still transmit the captured data only. This is little confusing. So let me repeat it again. D in data will only be captured until this load signal is applied. And once it's captured and load signal is deasserted, then the shifting operation will start on the captured data or the registered data, not on the D in data. Okay. Now for the shifting operation, we will use this shift enable input. And when this shift enable pulse is given, then the least significant bit or LSB will transmit out from the serializer module. And we will get the LSB at this output D output. And at the same time, when this shifting operation is happening, we will insert logical 1 at the MSB of our registered data. And once all the bits are transmitted, then this register will only have default state, means logical 1 at all the indexes. Okay, so that was a simple visualization of a serializer module. In the next session, we will write the VHDL code for this module. In the last session, we understand the functioning of serializer module. And now in this session, we will be writing the VHDL code for this. So this is the high level of our serializer module. We have three inputs: load, D in, and shift enable. And we have one output, D out. This D in input is a parallel data input, and this D output is a single bit output. So we will convert this parallel data into a stream of single bit, and then we will transmit each bit according to the specific baud rate. So we insert a load pulse, and when this load pulse is asserted, our shift register will capture the input data from this D input. And when this load signal is removed, our module will start shifting operation on the captured data, which is stored in this shift register. So we have this shift enable pin, and our module will shift the data every time it detects the pulse at this shift enable input. We will shift our data to the right by one position at each pulse of this shift enable input, and we will transmit the LSB of this register to the output D out. And every time it transmits a bit from the LSB, then after the transmission, this LSB data will be replaced by the next bit. And we will insert logical 1 at the MSB after each shift transmissions. And this process will repeat itself until all the parallel bits are transmitted one by one. So in our case, we have 10 bits to transmit, which include one start bit, 8-bit data width, and one stop bit. So we will need total 10 pulses. So let's write the VHDL code for this. Okay, so as usual, we will write our VHDL code on the Notepad++, and then we will simulate it on the Model Sim simulator. So for this, we will create a new file here in this Notepad++, and then we will save it as a .vsd file. So let's create a new file first. So go to File and create on New. Now save this file as .vsd. So go to File and click on Save As. So we will save this project in under the UART project folder. And here we have this source folder which we have created in the last session when we were designing our Baud Clock Generator module. So I will select this folder. Now give it some name. So this is our Serializer module. So give it the name Serializer. Now select the file type. So this file is basic hardware description language. So select this basic hardware description language file. So you can see we have this Baud Clock Generator file already listed here that we have designed in our last session. And now this file is Serializer. So just click on Save. Now we will write our VHDL code for this Serializer module. So first we will give the library declaration. So give it library IEEE use IEEE.std underscore logic underscore 1164.all. Now this is the time for entity declaration. So give it entity Serializer is port and entity. Now list all the ports for this serializer here. So first we will define clock and reset signal. So give it clock. So that is input type and this is std underscore logic. Now reset. So reset that is in std underscore logic. Now we will declare other important input output ports for this serializer. So give it. So if you remember from our previous session, we have 3 inputs and 1 output for this serializer. So we will declare all of them one by one. So first input is shift enable and this is std underscore logic type. So type shift enable and that is input type std underscore logic. Next we have load input. So give it load that is in and std underscore logic type. Next we have din, so that is input and this is std underscore logic underscore vector type. Now I need to give the range for this din input. For example, din data or our parallel data is 8-bit wide. So the range will be 7 down to 0, right? But if we write our code like this fixed range, then this VHDL code will be very specific for this data width. And personally, I don't like this. I want this code for any bit size. So what I will do that I will create a generic for this data width and then I will use that generic value for defining this range. So let's create the generic first. So we define the generic before this port declaration and inside this entity. So write generic. Now suppose this generic is data width. So write it data width and that is integer type semicolon. Now I can use this data width generic here in this din port. So what I will do that I will replace this hard coded value 7 with our generic value. So this will be data width -1 down to 0. And in the last we have output dout. So write it dout that is output type and std underscore logic. So this is our entity part. Now let's fix the alignment for these input output ports. Okay, so now this looks better, right? So this is our entity declaration. And for this, we have defined this generic for data width and we have defined the input output ports here. And now this is the time for architecture part. So write it architecture behave of serializer is now begin keyword and in the last and architecture means and behave. So this is our basic architecture template. Now in this section we will declare our signals and in this section we will define the function for this serializer module. So first we will write the functionality for this module, and then later we declare the necessary signals in the declaration section. Okay. So what we do that we will create a new process for this serializer module. So write it serializer process, and that is process. Now because this is a registered process block, so we will have clock and reset signal in the sensitivity list. So write it clock and reset. Now begin and end process. Now this is the basic template of process block. Now we will quickly write the registered process block inside this. So write it. So we have this reset condition first. So if reset is equals to 1, then do something, else if rising edge of clock, then do something, and end if. So this is the basic template for our registered process block. So what we will do that we will write our functionality here in this section of rising edge of clock. So if you remember from our last session, we said that when this load signal is asserted or when this load signal is 1, then our DIN data will be captured by this serializer module. And this DIN input is actually a parallel data, or you can say that is STD logic vector signal. And this parallel data will be shifted out to the output port, that is D out. Means this serializer will convert the parallel data from DIN input and convert it into the series of data, and then it will pass out to the output D out. Now this is important that the data will be shifted when this shift enable pulse is given to this serializer module. So simply we will write this logic here inside this section here. So we will write a condition that if load is equals to 1, then what will happen? That our DIN input data will be captured by some internal signal or this serializer. So suppose our internal signal is shift register. So shift register will get the value of DIN, right? Now when load is deserted, then it will look for this shift enable input. So we will write else if. Now when this shift enable is asserted, or when this shift enable pulse is given to this serializer, then what will happen? Then we will shift our data that is captured by this shift register signal to the right by 1 precision. So we will write that this shift register gets the value of 1 and means concatenation with shift register. Now we will use the array attribute to define this shift register range. So this will be DIN left down to 1. Now semicolon. And then we will terminate this if condition. So and if. Now there are few important things about this VHDL code. So first we will look about this 1 that we are inserting into the MSB of shift register. But before this, let's define this shift register in the declaration part of architecture. So define it. So this is a signal shift register, and this is std underscore logic underscore vector, and this will having the range of DIN. So we will use array attribute here. So it will be DIN range, right? Now semicolon. Okay, so let's understand what is happening in this statement here, because this is our main statement of this serializer. And this statement is actually shifting the data of shift register to the right by 1 precision. Okay, so let me explain that what is happening. So consider that our DIN is 4-bit wide, means it has 4 elements inside it. This means our shift register signal will also have 4 bits inside it, and the range will be 3 down to 0. So let me split this statement into individual indexes so that you can see that what actually is happening and how this statement is actually shifting the data to the right by 1 precision. So let's split this statement. Now treat these statements just like comment, and these are not part of this VHDL code. I'm writing them here just to explain this shifting operation. So as I said, this shift register is 4-bit wide, right? And the MSB is index 3. So we will have this shift register index 3. Now I will copy this. The next index will be shift register 2, then 1, then 0. So this is 2, this is 1, and this is 0. Now what I am saying that this shift register 3 will get the value of 1. So that will be our first bit, and that will pass to the highest index of this shift register, and that is 3. Next, what I am saying that this shift register 2 will get the value of shift register 3, right? And this shift register 1 will get the value of shift register 2. And this shift register 0 will get the value of shift register 1. And suppose our input value is 1010. So what will happen to this data when these 4 statements will execute for the first time? So first we will insert 1 at the beginning, and then we will get the value of shift register 3 at the second position. So it will be 1 again, because we have this 1 for this third index of shift register. Now the next value will be 0. So that will move for the first index here, and then we have this 1 at the first index. And now after shifting, that will be our index 0. So this will be 1. So this 1010 will become 1101 after this statement, right? So now the new value will be 1101. So write it 1101. Now what will happen? So first we will insert 1 at the index 3 of shift register, because we have this first value here, that is 1 at the MSB of shift register. Now the next value will be this index 3. So this is 1. So we will get 1. Now index 2. So this is our index 2 and the value is 1. So we will get 1 again. And now index 1. So this is 0. So we will get value 0 here. So this will be new data now. So that is 1110. So our new value is 1110. So when we shift this data once again to the right, so again 1 will be inserted at the MSB of shift register, then the index 3, so the value is 1. So we will get 1 at the second position. And now the second index, so the value is again 1. So we will get 1. And now this first index, and the value is again 1. So we are getting this 1 value. Let me add one extra row here. So when I load my D in input to the serializer, so shift register will capture the value of input D in, right? So the input is 1010. So the shift register value will be 1010. Now if we are using the RS-232 protocol, then according to the RS-232 standard, the least significant bit or LSB is transmit first and the MSB will transmit last, right? So in this case, when the value is 1010, our LSB is 0, means this value will transmit first, then this 1 value will transmit, and then this 0 value will transmit, and in the last this MSB or value 1 will transmit, right? So now look at this 0th index of shift register. So at the first pulse, when this shift enable pulse is given, so what will happen if we can transmit this 0 which is present at the 0th index of our shift register signal when this shift enable pulse is given to this serializer module. So at the starting, we will get this 0th value at index 0 of shift register. Then at the next pulse, when we shift our data to the right by the 1 precision, we will get this 1 value. And this will be the first index of our input data, means D in input. And for the next pulse, we are getting 0 at the 0th index of shift register. And if you notice, then this value 0 actually comes from the second index of our D in input. And when the fourth pulse is given, we are getting value 1. And this value 1 is actually the third index of our input D in. Means our input data, which is a parallel data, and we can get these parallel data to the output serially if we use the index 0 of our internal signal shift register. So 0, 1, 0, 1. Now this is the reason that why we have shifted our D in input or the shift register to the right by 1 precision. Because we have to transmit index 0 or the LSB of the data first, and in the last we will send or we will transmit the most significant bit or MSB. So what we will do that we will assign our D output whatever the value we have in the shift register at the 0th index, right? So we will write the statement that D out will get the value of shift register 0. So this statement will do the same thing which I have explained to you here in this example. Now there is one important question, that why we have inserted 1 here at the starting of shift register. Why we have not inserted 0 here, and if there is any impact if we use 0 here instead 1. So the answer is definitely yes. We have used logical 1 here because we are using RS-232 protocol standards, and according to that the start bit is always logical 0, and when your RS-232 protocol is not transmitting any data, means when it is in idle state, then it will have logical high value. So if you notice at the last transmission, means when this transmission is complete and all the bits are transmitted over the RS-232 protocol, then this value will indicate that now this is in idle state. But if you force 0 value here, then after the whole transmission is complete or all the bits are transmitted, then because of this 0 value, our transmission module will read this that we are getting a next data, and that is not correct, right? So we have used this value 1 instead value 0 here because our default state is 1. Now if you are working on some different protocol that have value 0 as in default state, then you will insert 0 here. Okay, so we can do one more thing here, that we can write this code for any default value. Means if default value is 1, then it will work accordingly. And for some another protocol, if the default value is 0, then this program will work for that as well. So what I will do, that I will replace this hard-coded value 1 with some generic value. And suppose this is defined as default state. So I will replace this 1 with default state. And everything is same. So let's define this default state in the generic section. So this is our generic section. And here we will define this default state. So default state, and that is std underscore logic type, right? Okay, so let's move down and delete all the extra lines which I have used to explain you about this shifting operation, right? So let's delete these lines from here. And we have one more thing to do, that is we need to define the reset condition. So what will happen when reset is asserted, that our shift register will get the value of default value. So our default value is 1, right? So what we will do, we will use others keyword like this. All the values will be 1. So this statement will assign 1 to all the bits or all the elements of shift register despite of its range. So if it is 4 down to 0, it will assign 1 1 1 1. If shift register is having 8 elements, then it will assign value 1 to all the elements. And now because we have defined a generic for this default value, so we will replace this 1 with the default state. So replace this with default state. Okay, so now everything looks good and our code for this serializer module is completed. Let's give a quick look that everything is fine. So this is library declaration, that is good. This is entity declaration and this looks good as well. We have defined generics here and then we have defined all the input output ports here. we have clock and reset as a general structure for a registered process or as part of a synchronous system. Then for this serializer, we have this shift enable input and load input, and both are STD logic type. We have this D in, that is input, and that is STD logic vector, and the range is data width -1 down to 0. And we have one output, that is D out, and this is STD logic type. And now we have this architecture section. So we have declared this signal shift register, and that is STD logic vector type and having the same range as D in input. So we have used array attributes here. Now begin, and we have used this serializer process. So we have this clock and reset in the sensitivity list. Now we are seeing that if reset is asserted or this reset is equals to 1, then shift register gets the value of others default state. So for this RS-232 protocol, the default state will be 1. So when this reset is high, all the elements of this shift register will get the value of 1. Now we have this else if condition. So this is the basic template of our registered process block. And inside this, we have this load condition. So when this load input is high, then our shift register will get the value of D in. Means when this load pin is high, our D in input will be captured into the shift register signal. And please note that the range of D in and the range of shift register must be same. Now we have the second condition inside this. So when this load signal is deasserted, means when this load signal is 0, then we will check for this shift enable pulse. And when this shift enable pulse is given, then we will shift the data of shift register to the right by 1 precision. And then in the last, we will assign the 0th index of shift register to the output D out. So this is our functional description for this serializer module. So now we will open the Model Sim Simulator and we will check this code for any syntax error. So open Model Sim Simulator. So Model Sim, enter. Let's maximize this window of Model Sim Simulator. So if you remember from the last session, when we have started working on this UART project, we have designed this Baud Clock Generator. So this was one module of our big system or this UART project, and we have the right code for the Testbench for this Baud Clock Generator. So both of these files are listed here. Now we are working on the same project, so we will import our serializer module here in this project. So what we will do that I will right click here and you will see the option of add to project. And now I will select this existing file because we have written our VHDL code for the serializer in Notepad++, and we are just importing it into this Model Sim Simulator. So click on this. Now browse the file. So our project is inside this UART project folder, and here we have this source folder where we have all the source file or all the VHDL file listed here. So we saved all of our source file here in this folder only. So we have written the code for this serializer this time. So select this and click on open. Now hit OK button. And now you can see that we have this serializer.vsd file listed here. And the status is question mark because we have not compiled this VHDL file yet. So first we'll compile this program. So right click and click on compile and then compile selected. So you can see the message here and it is saying that the compilation of serializer.vsd was successful. Means there is no syntax error. Okay, so now we will write the test bench for this serializer module. And then we will test it that if it is functionally correct or not. Means if it is converting the parallel data into the serial data correctly or not. And then if you are correctly getting the output at the D output, right? So in the next session, we will write the testbench VHDL code for this serializer module. So this was our VHDL code for this serializer module. And we have checked it for the syntax error as well. And our code is clean now. So in the next session, we will functionally check this module and we will write a test bench for this. And we will test that functionally our module is working correctly or not. In the last session, we have developed Serializer module and we have fixed all the syntax error in the code. Now in this session, we will test our Serializer module using a test bench. So let me brief some of the project specification first. First is system clock frequency, which is 50 megahertz in our case. Means 20 nanosecond will be our one clock cycle. Next is baud rate. So we will test it for the baud rate of 115200. Means 8.7 microsecond will be the timing gap between two successive pulses. We will test our system for 10 bit of data, which includes one start bit, 8 bit data width, and one stop bit. Now quickly talk about the test sequence. So first we will insert the reset condition for 100 nanosecond. After 100 nanosecond, we will disable this reset condition. Then we will give the load pulse for one clock cycle. At the same time, we will provide the D in data as AA in hex, means 10101010. Then we will generate 10 pulses at the baud rate of 115200, means at the gap of 8.7 microsecond. Okay, so that was a brief. Now let's move into the coding part. Okay, so in the last session, we have developed the VHDL code for that serializer module. And now in this session, we'll create the test bench for that serializer module. And we will test that if our serializer is working functionally correct or not. So let's move to the Notepad++ once again. So this is our serializer VHDL code. So we have this library declaration here. Then we have this entity declaration here. And then we have the architecture. If you have any doubt about this program or this VHDL code, then I highly recommend to watch my last session. Because in this session, we will write the test bench for this serializer module. So what we will do that we will create a new file and then we will save it at .vsd extension. So we will go to this file tab and click on new. Now as usual, we will save this file first as .vsd. So go to this file tab and click on save as. Now if you remember that we have the separate folder for our test bench file and that is inside this UART project folder. So you can see that we have this test bench folder here. So open this folder and now select the file type. So this will be basic hardware description language file. So select this option and you can see that we have this Baud Clock Generator _tv file and that we have written in the previous sessions. And now this is the test bench for serializer. So I will give the name that is Serializer _tb. TB is for test bench. Now click on this save button. So what I will do that I will go to this serializer file and then I will copy this part from this file. So this is our library declaration and entity declaration. So I will copy it and I will paste it to this serializer _test bench file. So paste this. Now because this is a test bench, so I will replace this entity name and that will be now serializer _tb. I will leave the generic declaration as it is here because we will be using this in some time, but I will remove this port declaration section here because this is a test bench and test bench do not have any ports, right? So I will delete this part and in the last and entity. So this is and serializer _tb. Now this is the time for architecture part. So write it architecture behave of serializer _tb is now begin and in the last and architecture. So and behave. Now first what I will do that I will declare the component of serializer here and we will declare all the input output ports of that serializer as a signal here in this test bench. So I will go to this serializer module and I will copy this entity part from here. So I will copy this and now I will go to this Testbench file and then I will paste it here in this section. So this is the declaration section of architecture. Now I will replace this entity keyword with the component keyword because now this is a component here. And same we will replace this serializer with and component keyword. And now everything is same. Now we will declare all of these input output ports as a signal here in this Testbench module. So I will copy all of these input output ports from here and I will copy them here in this declaration section. And now because these are signals in this Testbench, so declare them as signal. So what I will do that I will declare them as signals. So these are signal. Now select this option in selection and then replace all. Now remove the direction from these signals here because these are the signals, so they do not have any direction. So replace this in with colon. Now replace all and replace this out with colon. So replace it as well. Now close this and remove this line from here. So this is the extra line. Now what we will do that we will initialize this clock value with some initial data. So that is 0 for example. So I already explained that why we have initialized this clock signal only, not other signals. So I am not repeating much here in this session. If you really want to know about this, then please watch Baud Clock Generator Testbench session. I have explained this in detail there. But just a brief that we are going to invert this clock signal with the NOT gate to generate a clock pulse. And for that, we are needing some defined state. So that what it is doing, okay? Now, before driving these input output ports of Serializer, let's map the component of Serializer here in this Testbench. So I will copy this component part from here and now paste it here in the architecture section. Let's move this one tab further. So this looks better now, right? So first we will give some name to this component. Suppose the name is UUT or unit under test. Now remove the is keyword from here. Next, the first will be generic map. So write it generic map. Now the data width is suppose 10. So replace this with value 10 and now comma. And suppose the default state is logical 1. So this will be our logical 1. Now next is port mapping. But before this, remove this semicolon from here. Now port map. So clock is connected to clock, comma. Now let's copy this line here and paste it at every port of this component section. Now paste it and paste it. Now clock is connected to clock, reset is connected to reset, shift enable is connected to shift enable, load is connected to load, D in is connected to D in and D out is connected to D out. So this is our component mapping. Now before going further, let me standardize this code by defining the generic for this data width and for this default state. Now if you recall, then we have leave the generic part when I defined the entity declaration for this Testbench module. And these are data width and default value. So what I will do that I will give the default state here. So for example, data width is 10 and the default state is logical 1. So this is logical 1. And now I can use these generic data at this component mapping. So this will be data width and the default state will be default state. Okay. So now if I want to change the data width or the default state, then I do not need to come back here for updating the code. What I will do that I will just update the generic values here and all of the code will work accordingly. So that is the benefit of using generics in your VHDL code. Now important thing is that if you are not defining the generics here, but you are using the data width to define the range of your input port, then it will give the syntax error for your code. Why? Because this data width is expected to be declared first. So if you are not defining this in the generic section, then you have to define it as a constant. So you have to define this data width as constant, like constant data width, that is integer, and give it some value, suppose 10. So remember this, anything which you are using in your code, that must be declared first. Now both way is correct. If you declare this data width as a constant like this, or if you're declaring this data width as a generic. But if you write this as a constant, then it is somewhere in between the code, means between the architecture. But if you define this as a generic, then it is just at the starting of your code. So it is relatively easy to navigate to these generic values, but you can prefer any choice you want. Okay, so let's remove this constant line here because I will prefer to use generic here in this case. Okay, so now let's quickly brief the code first. So first we have this library declaration, and then we have this entity declaration. Okay, so at the same time I will align the text here so that it looks better. Okay, so this is our entity declaration, and now the architecture part. Now this code up to here, so these are the declaration for this test bench. So first we have declared this component serializer in this code, and that is having our generics. So we have two generics, data width and default state. And then we have these input output ports. So we have this reset and clock input port, and they are a steady logic. And for this serializer, we have this shift enable as an input, load as an input, and din again as an input type, but this is parallel data. So it is a steady logic vector and having the range of data width -1 down to 0. And we have one output dout, and this is a component, so AND component. And now we have this signal declaration. So all of these input output ports of this component serializer, they are listed as a signal here in Testbench. So they have the same data type as input output port of serializer component. Now in the architecture part, we have mapped the component with this Testbench signal. So data width is our generic, and it will get the value of data width, which is again generic in this Testbench code. And default state is default state. So this is 1 because we have defined this in the generic part, right? And next we have port map. So clock is connected to clock, reset is connected to reset, shift enable is connected to shift enable, load is connected to load, and din is connected to din. And the output port dout is connected to dout. And now here our component mapping is completed. So remove this AND component line. And now the main part is coming, and that is driving our input output signal. So let's say we are driving our signals here in this section of code. So first is this clock input. So I will write a simple code that clock is getting the value of not of clock after 10 nanosecond. Now, as I said that this statement will only work if you have initialized the clock signal. Like here that we have initialized this clock signal with the value 0. So if you not define it as an initial value, then your clock will be undefined. So when you invert your clock on any undefined value, then you will get the undefined value as an output. So remember this, that this statement will only work when you initialize your clock signal. Okay, so by using this statement, we are driving our clock signal. Now it is the time for driving the other input signals. So we have reset, shift enable, load, and din as an input signals or as an input port. And I will drive them inside the process block. So I will create a process for this. So let's give it some name first. So suppose this is main process. This is the process. Now, because this is a test bench and we are going to use wait statement inside this process block, so I will not use any sensitivity list here. So I will straight jump to this begin keyword and in the last AND process. Now because I have not used the sensitivity list, so let's use the wait statement. And this statement is very important here in this test bench, because we do not want to run this whole process inside a continuous loop. So once we drive all the signals, then we will hold our simulation, and that we will achieve by this wait statement. So this is very important. I have explained this in detail in the last session of Baud Clock Generator test bench. So if this is not clear, then please watch that video, because I have explained this in very details there. Okay, so now we will start writing this main process to drive our input ports of Serializer module. So first we have this reset input. So at the very starting, I want to give reset to my Serializer module. Means our reset should be high. So our reset will get the value of 1. Now it is always better that you specify all the input ports when you are initializing your simulation for the first time. So let's assign the values to all the inputs of this module. So we have this reset input, then we have this shift enable input, and suppose the value will be 0. Next we have the load input, and again the value will be 0. And next we have din. Suppose I am assigning logical 0 to all the elements of this din input. So what I will do, that I will use the others keyword. So others gets the value of 0. So what I will do, that I will assign logical 0 to all the elements of this input din. Now after initializing all the values, I will wait for some time. Suppose I will wait for 100 nanosecond. So I will write that wait for 100 nanosecond. And now what will happen after 100 nanosecond? That our module will come out from the reset condition. Means our reset will be logical 0. And now I will wait for another 100 nanoseconds. So wait for 100 nanoseconds. Okay, so now after this, I want to load my input data, so which is a parallel data, into the serializer. Means I have to assert the load signal. Means our load signal will be high. And at the same time, I will assign some value to the input port. So that is din. So I am saying that din will get the value of 10101010, means AA in the hexadecimal. Now because this is using RS-232 protocol, means we also have start bit and stop bit with this data bus. So I will include those bits as well. So our start bit is 0. So I will concatenate with this 0 value. Now I have inserted this 0 in the last here, because we have designed our serializer to transmit the least significant bit first, means LSB first, because our data is transferring in that manner. So I will follow the same rule here as well. Means our start bit is 0 and that will transmit first as an LSB. And our stop bit will be 1 and that will transmit at the last, right? So I will add 1 at the starting. So this 0 is the start bit, means logical low. Then this data will be transmitted, means LSB first and MSB last. And when all the bits are transmitted, then it is followed by stop bit. So that is 1 for RS-232 protocol. Now important thing is that you can write this din statement here before this load statement, or you can write this as it is. So don't be confused that I am loading the data first and then I am assigning some data to the input port. Because what will happen, that at the very starting, when your simulation is start, means at 0 timestamp, these all 4 statements will execute at the same time. Means all of these assignment will happen at 0 timestamp. Then it will wait for 100 nanosecond. And after 100 nanosecond, our module will come back from the reset state or reset condition. Then again, it will wait for 100 nanosecond. And then after that, both of these statements will execute at the same time. Although they are sequential statement, but they both are different signals. So the assignment will happen at the same time here. Now there is one very important thing before you assign these two statements here. And that is, we need to wait for the rising edge of clock after 200 nanosecond. So first this 100 nanosecond will wait until that time we have this assignment, and then for the next 100 nanosecond the reset is 0 and all other signals will remain same. So after this 200 nanosecond means 100 nanosecond here and then 100 nanosecond here, I have to wait for the next rising edge. So I will write the statement that wait until rising edge of clock. Now wait until because this is the expression or this is the change of state, and for that we use wait until. So remember this syntax, this is very important. Means if you are using any time window or time frame, so you will use wait for statement, but if you are waiting for some state or some condition, then you will use wait until statement, right? So wait until rising edge of clock semicolon, then only load will get the value of 1 and you will assign this value into the D input. Now we have used this wait until rising edge of clock statement because if you go to this serializer module, then you will notice that everything is happening inside this rising edge of clock. Means everything is synchronized at the rising edge of clock signal. So I have to use this wait until statement here, because if you do not use this, then your VHDL module can have stability problem, because flip-flops which is generated in the serializer for the registered block are needing some setup time. So I have to synchronize everything with the rising edge of clock in the test bench as well. Okay, so after this rising edge of clock, we have these two assignments. Now I will wait for another rising edge. So I will write this wait condition once again. So that is wait until rising edge of clock. Then what will happen that our load input will get the value of 0. Why? Because we need to capture our input port or our input data for one clock cycle only. And once it is captured by the serializer module, then it will start transmitting the data one by one. So one clock is enough to load the data or to capture the input data, which is present in the D input. Now you can assign some default value to this D input, although this is not required, because this D in data will only capture when load is high or this load signal is high. But now this load signal is 0, so it really doesn't matter that what value we have at this D input. But as a safe side, let's assign the default data of D in here at this timestamp. So D in will be others gets a value of 0. Okay, so till now what we have did that we have give the reset condition first, and at the same time we have initialized other inputs at 0 timestamp. Then we waited for 100 nanosecond, and after 100 nanosecond we have deasserted the reset signal, and then we waited for another 100 nanosecond. Then we waited for the rising edge of clock signal, and at this first rising edge of clock we have assigned value 1 to the load signal, and at the same time we have assigned some value to this D input. So actually the data is AA in the hexadecimal, and this 0 as an LSB is your start bit and 1 as an stop bit. So we have total 10 bits here in this D input, and this data will load at this timestamp. And now we waited for the another rising edge of clock, and at this timestamp we deasserted the load signal and assigned the default value to the D input. And now the most important part is coming. Now we need 10 pulses to this shift enable input or this shift enable signal, because we have 10 bit of data to transmit over the RS-232 protocol. So we will generate 10 pulses for this shift enable signal. Now because we are using RS-232 protocol, so we have to very specifically design the timing specifications, because the pulses will only generate at the fixed duration of bit period, and this bit period is actually defined by the baud rate. So first we will generate the shift enable pulse. So what we will do that we will wait for the rising edge of clock, and now when this will happen, then our shift enable pin will get the value of 1. Now for the another rising edge, our shift enable pin will be 0. So what it will do that for the first rising edge, the shift enable pin will be high, and for the very next rising edge, our shift enable pin will be low. So these 4 lines of statements will give 1 pulse on shift enable. Now the problem is that these pulse will be generated at every rising edge. Means in our case, this clock frequency is 50 MHz. Means these pulse will be generated at every 40 nanosecond. And we do not want this because we are working on the baud rate of 115200. Remember, we have designed our Baud clock generator at this baud rate frequency. So our bit period will be 8.7 microsecond for the baud rate of 115200. I have explained this that how you can calculate this bit period from the baud rate. Simply divide the baud rate from 1 second and you will get the bit period. So this means that we need to generate this shift enable pulse after 8.7 microsecond. So what we will do that we will wait for 8.7 microsecond. So now first we will wait for the 8.7 microsecond and then it will generate 1 pulse at this shift enable. And now we are needing 10 pulses of this shift enable, right? So what I can do that I can copy these line of statements here and then I can paste it multiple times. Means in our case we can type it for 10 times because we are needing 10 bits of transmission. So we are needing 10 pulses at this shift enable. So that is one way of doing. But what I will do that I will use the loop statements here. So instead of writing these statements multiple times, I will write these 4 statements inside a for loop. So I will say that for I in 0 to 9 loop, and now all of these 5 statements will run in the loop of 10 and in the last AND loop. Now because we have already defined the data width in the generic part, so instead hardcoding this 9 value, I will use our generic data. So that is data width. So I will use this generic here. And now this loop will generate 10 pulses of this shift enable signal, right? Okay, now let's save this program and let's quickly see if everything is good. So this is library declaration, that is good. This is entity declaration and we have defined the generics here. And the value of generic is 10 bit for data width and the default state is 1, so this is good. Now architecture part. So first we have defined this component, so this is good. And now we have declared all the signals and that is also good. We have also defined this data width as a generic and we have initialized this clock signal with value 0. Now first we have derived this clock signal. So this clock will be not of clock after 10 nanosecond. So it will generate 50 MHz of our clock frequency and that is same as our FPGA board frequency. Now we have this main process here. So at the very starting means at 0 timestamp we have these 4 statements. But the main thing is that reset is high and now after 100 nanosecond this reset signal is deasserted and then we will wait for another 100 nanosecond. Now for the next rising edge, we will load our D in input data into the serializer and for the very next rising edge of clock, this load signal will be deasserted and our D in signal will also 0 or it will get assigned with the default value. Now here we are generating 10 pulses for this shift enable. So we have used this loop. Now first we have used this wait for 8.7 microsecond so that it can generate pulses at the baud rate of 115200. So for the one rising edge we have this shift enable high and for the next rising edge we have this shift enable 0. Now if you remember that we have designed the whole module for these few line of statement because this is the same task that we were doing into the Baud clock generator. So you can see that this whole line of VHDL code is actually generating the same pulses like these few lines of codes Because we have used wait statement here and we are very specifically controlling the time period. So this is the beauty of wait statement. But the problem is that this code is not synthesizable. Means you cannot implement this on FPGA board. But this is fine because we are using this Testbench module only for the simulation purpose. And we are doing the simulation on the simulator tool virtually on our PC. Okay, so then we have completed the process, and in the last we have this component mapping. So UUT is our unit under test, and this is the component of serializer. Then we define the generic map. So data width is having the value of data width, default state is default state, and now port mapping. So all of these ports are defined to the same name as the signal of this test bench. And in the last, AND architecture. Now, if you want to test the same module with more set of inputs, then you can also create another copy of this component here. So like this. So suppose this is DUT and you have mapped with some another signal. So this is clock 1, reset 1, shift enable 1, load 1, T in 1, T out 1. And you can define these signals in the declaration part of this test bench. But in our case, we are just using one single unit to test our module. So let's save this code. And now we will move to the model sim simulator. So we will open it. And now again, right click here. Now select this add to project option. Now click on existing file. Now we will browse the location of our test bench. So click on browse. Now all of our test bench modules are present in the separate folder inside this UART project. So we have this test bench folder. We will open it. And now we have just written the code for this serializer underscore TB here. So I will select this and now open. Now click on OK. So you can see that this serializer underscore TB.vhdl file is listed here. And the status is question mark because we have not compiled it yet. So right click on this file and click on compile and then compile selected. Okay, so you can see that it comes with some error. So just double click on it and now make it little wide so that we can see that what is the error. Okay, so it is saying that at this line number 43, it is expecting semicolon. So let's move to the Notepad++ and look at this 43 line number. So this is the 43 line number and we have this signal D out, that is std logic, and we have missed to add semicolon here because we have copied it from the entity section and that do not have semicolon in the last. So I will add it up here and I will save this file again. Now move to the model sim simulator. Now close this window. Now again select this serializer underscore tb.vsd, right click, compile and compile selected. So you can see that compilation is successful and we are getting the message that compile of serializer underscore tb.vsd was successful with some warning, but we will ignore these warnings here. Okay, so you can see that everything is right ticked in this status section. So now we will move to this library tab here. And as I said that what is important for us, that is work library here. So I will expand this and you can see that we have all of our modules listed here. So these are listed here because we have successfully compiled all of these VHDL file here. So all of these things are listed here in this work library. Okay. So we will simply select this serializer underscore TV, then right click and click on simulate. And now if everything goes well, then you will see this kind of window. Now you can see that we have couple of tabs here. So that is data flow and wave. So we will switch to this wave window. Now, just in case if you are not getting this window, then simply go to this view tab and here you will see this waveform window option named as wave. So you can see this is selected here, but if you unselect it, so you can see that this type of window. So waveform is gone here. So to take it back, go to the view tab again and now tick this waveform window or this wave option, and you will see this waveform window here. Now this is the object window and this is the instance window. So you can see that serializer underscore TB is selected here, and all of these objects are actually the signals of this serializer underscore TB. So you can see that all of these are signals and these two are generic. But I am not really interested on these signals of this serializer test bench. I am more interested in this UUT. So that is our unit under test. So if you select this UUT, then this object window will display the input output ports and the signals of this UUT, not of this test bench file. So you can see that this is clock and this is input type, data width is input, and this is generic. Default state is generic and input type. Same D in, that is input, and this is a signal. Same D out, that is output type. Load input, reset input, shift enable input, and we have this shift register signal, and that is internal signal. So what I will do, that I will select all of these objects other than this data width and default state, because these are generic values and they are not going to be changed in any case in our modules. And you can see the value of it. So data width is 10 and default state is 1. So I do not need them into the waveform window here. So I will simply select all of these objects from here other than this data width and default state, and then I will drag them here in the waveform window. Okay, so let's make it little wide so we can see that what are these inputs. And now we will simulate our test bench. So I will use this transcript window here. So what I will do, that first I will run my simulator for 1 microsecond. So give the command that is run for 1 microsecond. Now move to this waveform window and let's zoom out little so that we can see everything. So we will move to the initial stage and let's see that what is happening here. So this is our clock input and this is 50 megahertz clock frequency, means the clock period is 20 nanosecond. So just quickly check it. So this is our 0 timestamp, and now this is almost 20 nanosecond. So if you zoom in little, so you can see the exact time. So this is the 20 nanosecond, right? So you can see this is 20 nanosecond, means this is 50 megahertz of clock frequency. So this is good. Now zoom out little. Now we have asserted reset signal for 100 nanosecond, right? So let's move this reset signal at the top, something like here. Now let's move load input next to it. Now move this shift enable here. Okay, so the sequence is much better now here. So first we will jump to this 100 nanosecond here. So you can see that this is high. So this reset signal is high up to this point. And at this 100 nanosecond, this reset signal goes to low. Okay, so this is 100 nanosecond. So this is 100 nanosecond. And now this reset signal is low. Okay. Now we have waited for another 100 nanosecond, means total 200 nanosecond from here. So this is 100 and now this is 100. So this point is another next 100 nanosecond. So you can see at 200 nanosecond, we have waited for the rising edge. So this is the falling edge and we have the rising edge at this particular time. So at this particular time, we have this load signal which is high, means we asserted the load pulse at this particular timestamp at the rising edge of clock after waiting for 200 nanosecond of time period. And you can see at the same time we have the input value, that is 10101010, and the last 0 is our start bit and this first one is our stop bit. So you can see that when this load is high, at the same time we have this D in input. Now at the next rising edge of clock, this load signal is deasserted. So you can see the value of load signal is 0 here. And now the DN signal is all zeros. But if you notice that at this timestamp when this load signal is 0, we actually moved our D in input to this shift register. So you can see now the shift register value is this one. So let's expand this. So you can see all the individual indexes listed here, and it is the same value like this D in. So it is 1101010100. So you can see this is 1101010100. Means we captured the D in data when this load signal is asserted, right? Now let's look at this D out. So you can see that this D out was logical high up to this time period, and now at this stage this becomes 0 because our D out is actually the LSB of this shift register. So if you expand this and if you look at the 0th index, then the value is 0. So we are getting this LSB value means 0 at this output. Okay, so this is functionally correct. Now we have to look at the 10 pulses which we will get at this shift enable pin, and that should be at baud rate of 115200. Means at every 8.7 microsecond we should get this shift enable pulse, right? So for this, let's zoom out this window, and now we have to run our simulator for larger time. For example, let's say that we will run our simulator for 100 microseconds. So run for 100 microsecond. Okay, select this waveform window and zoom out. Okay, so you can see that we are almost get 10 pulses here, but let's run our simulator for another 20 microseconds. So write the command that is run for 20 microsecond. So you can see that nothing much is happening now because all of the 10 pulses are generated here. So up to this time we have all of the 10 pulses. Okay, so let's count it first. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we are actually getting 11 pulses here. So if we move to our code and if you look at the loop, so we have used for I in 0 to data width loop, and this data width actually 10. So our loop is moving from 0 to 10, and that is having 11 pulses. So I have to use data width -1 here. Okay, so I will save this. Now again go to this model simulator. Now go to this project tab. Now select this serializer underscore tb.vsd and then compile once again. So compile selected. So compilation has been successful. Now restart this simulation. Click on OK. Now simply run this simulator for 150 microsecond. So run it for 150 microsecond. So 150 microsecond. Okay, now let's count the pulses. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, right? Now quickly move at the starting. So let's zoom in little and jump to the starting of the simulation. So we have already covered this. So this is reset. So for 100 nanosecond, almost here, the reset is high. And then after 100 nanosecond, reset is low. So this is low after this 100 nanosecond. So you can see that up to this 100 nanosecond of time, this reset signal is high. Okay, so this is high. And at this point means after 100 nanosecond, this reset signal is low. Okay, so you can see that this reset signal is low. And now after another 100 nanosecond means at this point, now we are waiting for the rising edge of clock. So this is the falling edge, and the next rising edge is this point. So at this point, our load signal is high, and at the very next rising edge, this load signal is low. Okay, so you can see that at this point, our day in input is 1101010100. And when this load signal is asserted, then at the next rising edge, we are getting this value at this shift register. And according to this shift register, we are getting the output at this D out. So because this shift register is having the value of this and its 0th index is having the value of 0, so that is why we are getting this 0 at this output D out. Next, let's zoom out this window and let's move to this first pulse. So you can see that this shift register data has been shifted to this value. So you can see that this 1 is inserted here and rest all of the data is shifted to the right by 1 precision. Now at this point, again our 0th index of shift register is 0. So we are still getting 0 at this output D out. Okay. Now at the next pulse of this shift enable, now again the data is shifted by 1 precision and 1 is inserted here at the starting and all of the data is shifted to the right by 1 precision. And now the index 0 of this shift register become 1. So you can see that our output is now set to high. So this is our output and now this is high. Now if we select to the right, so at this particular timestamp, we are getting next pulse at this shift enable. So you can see we have this next pulse and now our shift register value is this one and the index 0 is 0. So our D output is 0. So you can see for this period, this is 0. Now for the another pulse, D out value is 1 because this shift register at the 0th index is 1. So like that, we are getting total 10 number of pulses. And at every pulse, we are getting 1 bit of our input D in. And that output is sequential. And we are getting least significant bit or LSB first. And then we are getting the most significant or MSB in the last. So if you record this value, that is 1101010100, we will get 0 at first pulse, then again 0 at second pulse, then 1 at third pulse, then 0 at fourth pulse, 1 fifth pulse, 0 sixth, 1 7th, 0 8th, 1 9th, and again 1 at 10th. So let's see at the output. So 0, 0, 1, 0, 1, 0, 1, 0, 1 and 1 means functionally our serializer is working correctly. But there is one important thing to test here, and that is baud rate. Means we have to test that we are getting the pulses at the right time or not. Means for the baud rate of 115200, we should get the pulses at every 8.7 microsecond. So let's see. So we will select any two successive pulses, for example this one and this one. So what I will do that I will create a new marker and then I will slide it at the one pulse and I will zoom a little. Okay, so this is our one pulse. Now create another pulse. Now move the slider to the another pulse. Okay, so we have this pulse here. Okay, so we have both of the markers which are pointed to two successive pulses, and now we will see the timing gap between these two pulses. So let's zoom out little and we have these two pulses here. So you can see that first pulse is at this point of time and the successive pulse is at this particular point of time. And you can see the time difference between these two markers is 8738 nanosecond. So this value is actually in picosecond. So this is macrosecond, means 8730, and now this is in nanosecond. So 8730 nanosecond, and if you convert it into microsecond, so it will become 8.7 microsecond. This means that our bit period is actually correct for the baud rate of 115200. Although this figure is not exactly 8.7 microsecond, but this is fine. And this is because we are waiting for the next rising edge of our system clock frequency. So it is slightly higher than 8.7 microsecond exact. But this is inside the offset variations of RS-232 protocol. So this is completely fine. And now I am pretty satisfied with the results here. So till now we have completed Baud Clock Generator. Then we have created the test bench for that Baud Clock Generator. And now we have completed Serializer module, and in this session we have tested our Serializer functionally as well. So now we have both the modules ready for the UART transmitter. So in the next session we will combine both of these modules and then we will create the UART transmitter which will use RS-232 protocol for the transmissions. And then we will write the test bench for that module so that we can test it functionally. So that was our serializer module, and I'm pretty satisfied with the results as this is doing the things as we are expecting from it. We have fixed a couple of functional issues during this simulation process. So you can go through that how we test our modules functionally and how we detect the issues and how we fix them. So I hope it's helpful to you. So that was the second component of our UART transmitter project. And now it's the time to combine both of these modules to develop a UART transmitter. And then we will start working on the UART receiver. In the last few sessions, we have designed Baud Clock Generator and Serializer module for our UART project. And we have simulated them and tested them as well. Now today, we will merge these two modules to design our UART transmitter. Means we will use Baud Clock Generator, which will generate pulses to drive the serializer module based on very specific bit period, which is calculated from our system clock frequency and our baud rate. So in this example, we will use 50 megahertz of system clock frequency and the baud rate will be 115200. Although you can simply change them based on your design requirements because our VHDL code are flexible enough to work on any combination of baud rate and system clock frequency. So this is the structure of our UART transmitter module. You can see we have two modules here, which we have already developed. And these are Baud Clock Generator and the another is Serializer. If you are not clear about these two modules and their VHDL codes and test benches, then please watch the previous sessions. Because in this session, we are going to interconnect these two modules. So you can see that this UART transmitter module has two input ports, and these are TX start and TX D in. TX D in is our parallel data, which we are going to transfer over the RS-232 protocol. TX underscore start is the input port, which will tell our module that when this module should load data and when it should start transmission. Means when this TX start pulse is asserted, then our input data will load into the module. And when this TX start pulse is deasserted, our module will start the transmitting data, right? Next, we have two outputs in this module. One output is our transmitting bit or transmitting data, and another output is TX ready. TX underscore ready will indicate that either our module is ready to capture any input data or not. Because if our module is busy in transmitting the data, then this output should be low, which will indicate that our module is busy in transmitting data and it cannot take any new data at this moment. And of course, we will have clock and reset ports. Now, if you look at this structure, then you can see that our TX underscore D in is connected to the D in port of our serializer. This TX underscore start is connected to the load port of this serializer. And it is also connected to the start port of our Baud Clock Generator. Now our output port TX underscore D out is connected to the D out port of serializer. And our TX underscore ready output is connected to the ready port of Baud Clock Generator. So these are our input output port mapping. But we have also few ports pending of serializer and Baud Clock Generator. And we will connect them by using the internal signal. So we have this TX underscore Baud Clock signal, which is connected to the Baud Clock output of the Baud Clock Generator and a shift enable input of the serializer module. So this is a very simple structure. And now we will write this into our VHDL code. So let's move. Okay, so you can see we have 4 different VHDL files here, which we have written in the previous sessions. So this one is for serializer, And we have written the test benches for this serializer in this VHDL code here, right? Then we have the another VHDL code for this Baud Clock Generator here. So this is the code for Baud Clock Generator. And we have tested this module using this Baud Clock Generator Testbench VHDL code. Now in this session, we will combine both of these modules. So that is Serializer module and another is Baud Clock Generator. And by using these two modules, we will design our UART transmitter. So what we will do that we will create a new file and now we will save this as a .vsd file. So click on File and then Save As. Now first I will select the file type. So that is VHDL file, right? And the extension is .vsd. So select it. So this is the format, that is basic hardware description language. Select this. Now you can see that we have two testbench files listed here that we have written in our previous sessions. As we did in our previous sessions, that all of our VHDL module file are listed in the source folder, right? So we have this source folder listed here. So double click on it and now we will save this file here at this location. So give the file name and the file name is suppose UART TX for transmitter, right? Now click on Save. Now first we will give the library declaration and then entity declaration. So for this I will use this serializer file and then I will copy this part from here and then paste it here. So we have this library declaration here and we have this entity declaration here. So we will modify the content of this entity with our UART transmitter module, right? So we will replace this serializer with our entity name. So this is UART underscore TX. Now copy this. So UART underscore TX and then replace this and serializer with and UART underscore TX. Now we will quickly write the architecture body as well. So architecture behave of UART underscore TX is then begin and in the last and architecture means and behave. Now let's define the input output port for this UART underscore transmission module. So we will need this clock input and reset input in this UART transmission module as well. So I will leave these two inputs as it is. Now let's define the other input output ports for this UART transmission module. So first is start pin. So let's give it some name. Suppose this is TX underscore start, right? So this is input type and std underscore logic. So this is correct. Next we have this D in input, right? So let's remove this load from here for now. And we have this D in as a second input. Now let's change its name to TX underscore D in. And this is input type std logic vector and data width -1 down to 0. Now for this top module, let's change this generic name to TX underscore data width. And I will do the same for this generic here. So this is TX underscore data width here. So this is good. Now we have another port and that is output type. So that is dout. So let's change its name to TX underscore dout. And that is output type and std underscore logic. Now semicolon at the last. And we have one extra output that is transmission ready. So TX ready. So that is output type and this is std underscore logic, right? So these are all input output ports for this UART transmitter module. So we have this library declaration here and we have this entity declaration here. Now this is the part for generics and this is the part for port declaration. So at the moment we do not need this default state. So I will remove this from here and now that looks good. So let's jump to the architecture part. So this VHDL code is actually very simple because what we will do in this code, we will use our Baud Clock Generator and our Serializer module as an component here. And we simply connect its port according to this UART transmission module, right? So for that, first we need to declare Baud Clock Generator and Serializer as a component here in this UART transmission module, right? So for this, what we will do that we will copy this Baud Clock Generator entity. So let's copy this. Now go back to this UART transmitter module. Now here after this architectural declaration line and this begin keyword, we will declare both of our components. So let's paste this Baud Clock Generator as a component here. So replace this entity keyword with the component keyword because this Baud Clock Generator is a component here, right? So this is a component, and in the last we will replace this Baud Clock Generator with the component keyword. Now we will do the same thing for Serializer module. So we will copy this entity part of this Serializer and then we will paste it here in the declaration part of this UART Transmitter module. Now again we will copy this component keyword and I will paste it or replace this entity keyword with the component keyword. Same I will do at the AND Serializer. So now this will be AND component. Now we will interconnect all of these input output ports of these two components according to the UART transmitter module, right? So for this I will copy this whole part from here. So I will copy this and paste it in this section of architecture. So now we will give the port map and generic map for this Baud Clock Generator first. So update this part with port mapping and generic mapping for this Baud Clock Generator. So first we will give the instance name. So give it some name. For example, this is Baud Clock instance, right? And this is a component of Baud Clock Generator. Now remove this is from the last. Now we will use keyword generic map for generic mapping and same for port map for port mapping. So this is port map. Now our data width will be same as our transmitter data width, right? So this will be our transmitter data width, so tx underscore data width, comma. Now our system clock frequency will be 50 megahertz, so this will be 50 megahertz, so 50 000 comma. And now let's give the baud rate. So this will be 115200, right? Well, this is completely fine if you're only working with this clock frequency that is 50 megahertz and this baud rate that is 115200. But if you want to make your VHDL code more flexible, which can support diversified system clock frequency and different baud rates, then we will recommend to use generics here, right? So this system clock frequency will be our transmitter system clock frequency. So this will be transmitter system clock frequency and this baud rate will be our transmission baud rate, okay? And now we need to define these two generics in the generic section of this code. So this is here, enter, paste. So this is transmission system clock frequency and this is integer type semicolon. And now we have the third generic, so that is tx underscore baud rate, okay? So that is again integer type, right? Now quickly arrange them in a better way so that they can look better. Same I will do to this port declaration part as well. Okay, so this looks better now, right? Now come back to our component part. So this is our generic map, right? And now we will map our ports. So this clock will be connected to the system clock. So this will be connected to our clock, comma. Now this reset will be connected to reset. This start pin will be connected to the transmission underscore start. And now we need to connect this baud clock. So this will be connected with our baud clock, right? Although this is not an input output port for this transmission module. So this baud clock will be act as an internal signal for this transmission module. And we will define this signal sometime later. But for now, let's say that this baud clock is connected to this baud clock. Or even we can say that this baud clock is connected to transmission baud clock. And we will define this tx underscore baud clock in some time. And now we have this ready output. So this will be connected with our tx underscore ready output, right? Okay, so that's complete our component mapping. So let's move this AND component part from here and remove this semicolon from generic map. So this is our component instance for Baud Clock Generator. Now we will do the same for the serializer. So this is our serializer module. And now we will map its generics and ports according to this transmitter module. So first we will give some name to this. So suppose this is serializer underscore instance. This is component of serializer. Now remove this is from the last. Now write generic map. So this data width is our transmission data width, comma. Now we have this default state. Now for RS-232 protocol, we have 1 as in default state. So what I will do that I will mark it 1. Although you can also create a generic for this default state. But we know that we are working on the RS-232 protocol. And for this protocol, the default state is always 1. So this parameter is something that is not changeable for this RS-232 protocol. So there is no need to define this as a generic. So instead, I have hard coded this with logical 1. Now we will give the port map. So let's remove the semicolon from here and now write port map, and now this clock signal is connected to our clock, comma. This reset is connected to the reset pin. Now comma, this shift enable is connected to, now if you remember from the serializer module, then this shift enable pin is actually the pulses which was used to enable the shifting and transmitting the bits sequentially. And for the baud rate of 115200, we have generated the pulses at the time gap of 8.7 microsecond, right? So this pin is actually the bit period of baud rate. And for this module, this is shift enable pin will be connected to this TX underscore baud clock. So you can see that this Baud Clock Generator will generate this TX underscore Baud Clock because this was the output port for this Baud Clock Generator module. And now this TX underscore Baud Clock will drive this shift enable of serializer in this UART underscore TX module, right? Next, we have this load input, right? So what will happen that when you start your UART transmission, then your data at the input will load to the serializer, right? So for this UART transmitter module, this will happen when you apply TX underscore start pulse. So this load will be connected to our TX underscore start pin, right? Now next input is D in. So this will be connected with our TX underscore D in, and our output is connected to TX underscore D out, right? So this completes our port mapping as well. Now we have one small problem here, and that is because we have this TX underscore data width which will define the size of our input data. But this RS-232 protocol has two extra bits, that is one start bit and one stop bit, right? So we need to generate two extra pulses from the Baud Clock Generator. So what we will do that we will move to this component section of this Baud Clock instance, and we will say the data width for this Baud Clock Generator is TX underscore data width plus 2. So this TX data width is 8, means 8 bits, and then plus 2. So 1 for start bit and 1 for stop bit. So now this data width will be 10. Same way we will have 10 bits to transmitter for this serializer. So we will do the same, that data width will be our TX underscore data width plus 2, right? Now in this component mapping, we are saying that this D in is connected to the TX underscore D in, right? But this TX underscore D in is 8-bit wide because that only contains the data bits, which do not include the start bit and stop bit. So let's create another signal and let's name this TX underscore packet. And this TX underscore packet is our start bit, so which is 0 here. Then our data bits, which is TX underscore D in, and then concatenation with stop bit. But we have the small problem here. If you write this start bit, then data width, and then stop bit, can you guess what it is? So the problem is that RS-232 protocol transmit the least significant bit first, means LSB. So in this case, this 1 is our LSB. And that is wrong, right? Because our start bit is 0. This means we need to transmit 0 first. So what we will do that we will replace this 1 with 0. So this will be transmit first, and that is our start bit. Then it will be followed by the data bits, and in the last stop bit, which is 1. So this is the correct way of writing. Okay, so this completes the code for architecture part as well. Now we will define the necessary signals for this UART underscore transmitter module, which we have used in our architecture section. So we have this TX underscore baud clock, which we have used here. So this is a signal here. So this is a signal TX underscore baud clock, and that is STD underscore logic type, right? We have another signal, and that is TX underscore packet, right? And that is STD underscore logic underscore vector. Now the range will depend on this data bit, right? So if you are transmitting 8-bit data, then this transmission packet will be 10 bits because 8 bit is your data bit, 1 bit is your start bit, and another 1 bit is your stop bit. So our data range will be data width plus 1 down to 0, right? Means if your data width is 8, then your range will be 9 down to 0. Means total 10 number of bits, right? Okay, so I think we are done with our VHDL code for this UART underscore transmitter module. So we have this library declaration here. Then we have this entity declaration here, which is having 3 generic values, that is TX underscore data width, TX underscore system clock frequency, and TX underscore baud rate. And all of these generics are of integer data type, right? Then we have this port declaration. So these clock and reset are standard. Then we have this TX underscore start as an input type and STD logic. We have this TX underscore D in, that is input type, which is STD logic vector. And the range will be TX underscore data width minus 1 down to 0. Next, we have this TX underscore D out, that is output type and STD underscore logic. And in the last, we have this TX underscore ready, and that is again output type and STD underscore logic. So that's complete our entity part. And now this is the time for architecture. So we have this architecture. Here we have declared both of our components, that is Baud Clock Generator and Serializer. And we have also declared signals here, that is TX underscore baud clock and TX underscore packet. Now the VHDL code is very simple. We have this first instance, that is Baud Clock Generator. So this is component Baud Clock Generator. So here first we have given the generic map. So this data width will be transmission data width plus 2. So we have 2 extra bits because one is start bit and another is stop bit. We have this system clock frequency, and that is transmitter system clock frequency. And this baud rate is your transmitter baud rate, right? Then we have this port mapping. So clock is connected to clock. Reset is connected to reset. Now our start signal is connected to this transmitter start. We have connected our baud clock with the transmitter baud clock, and then ready is connected to this transmitter ready. So this is our Baud Clock Generator instance. And now we have this Serializer instance. So this is straight again. Data width is TX data width plus 2, and default state is hard-coded 1 here. Now port map. So clock is connected to clock. Reset is connected to reset. Now shift enable, which is our bit period according to the baud rate. So we have connected this shift enable to this TX underscore baud rate, and that will be generated from this baud clock instance, right? And now this load input is connected to the TX underscore start. Our D in is our TX packet, and we have defined this TX packet here in this line, which is your start bit at the starting, which is your LSB, followed by your data bits, and then stop bit in the last, right? So this D in connected to this TX underscore packet, and our D out is our TX D out. Okay, so let's save this code. And now we will check the syntax for this UART underscore transmitter module. So for this, we will open Model Sim Simulator. So open it, Model Sim. Okay, so let's maximize this. Okay, so this is question mark. So let's compile it first. Compile all. Okay, so we have already created this project and we already created this serializer and Baud Clock Generator in our previous sessions. And we have test benches for these two modules as well. And now we will import this UART underscore TX module we have just written here. And then we will compile this program to check if there is any syntax error or not. So simply right click. Now click on this add to project and click on existing file. Now click on browse. Now go to the source folder under this UART underscore project. So we have this source folder and this is the UART underscore tx.vsd file which we have just written. So I will select this file and I will click on this open button. Now click on OK. So you can see that this UART underscore tx.vsd file is listed here. So right click and now click on compile and then compile selected. Okay, so we have couple of errors here. So let's see that what are these. So just hover the mouse over these three errors and now double click on it. Okay, so let me make this little wide. So it is saying that every error is on this line number 62 and that is unknown identifier data width. So let's move to our VHDL code and look at this 62 line number. Okay, so this is our 62 line number. Okay, so it's right because this data width is actually tx underscore data width in this UART transmitter module, but we have used data width. Okay, so let's save this file once again and go to this Model Sim Simulator. Now close this. Now select this UART underscore tx file, right click and then compile selected. Okay, so you can see that the compilation is completed and this is successful. And you can see the right tick here as well. Now we will write the test bench for this module and then we'll simulate it into the waveforms and we will see that functionally this is correct or not. So that was the VHDL code of our UART transmitter module and we have fixed all the syntax error in our code. But this does not mean that functionally it is correct, right? So now we will write a test bench to test this module and we will validate everything like reset condition, D in load, start bit transmission, data transmission, stop bit transmission, number of bits transmitted, bit period of our design, Baud clock calculation, etc. In the last session, we have written the VHDL code for our UART transmitter module. And now this is the time when we will functionally test our VHDL code. So in this session, we will write the test bench to test our module. And we will validate everything like reset condition, D in load, start bit transmission, data transmission, stop bit transmission, number of bits transmitted, bit period of our design, baud rate calculations, etc. So first, quickly look at this structure. We have two inputs, tx underscore d in and tx underscore start. And we have two outputs, tx d out and tx ready. And we also have clock and reset port. We already explained the structure in the last session, so we are not repeating it again here. But in brief, we will test our module for 50 MHz of system clock frequency. And the baud rate will be 115200 for this design. So our data bits will transmit at every 8.7 microseconds. Now let's brief our test sequence. So we will start from the reset condition. So our reset will be asserted for 100 nanosecond. Then we will remove the reset condition for another 100 nanosecond. Next, we will load our input data into the transmitter module for 1 clock cycle. And after that, our transmission of data should start and each bit must be transmitted at every 8.7 microsecond. So this is our simple test sequence. So let's write the VHDL code for this test bench. Now we will write the test bench for this module, and then we'll simulate it into the waveforms, and we will see that functionally this is correct or not. So let's move to the Notepad++ once again. Now I will create another file for UART_TX test bench. So we will create a new file. Now first I will save this as .vsd. Now as I told you that all of my test bench file are placed at this test bench folder, right? So I have selected this folder and then select our file type. So this is VHDL file, so .vsd. And we have this basic hardware description language file, and you can see we have Serializer_testbench and Baud Clock Generator_testbench already listed here. Now we will create UART_TX testbench. So I will name it UART_TX_TB. Now click on save. Okay, so now let me copy the entity and library declaration first of this UART_TX module. So let's copy this part and now paste it here. Now complete the architecture body. So this is begin and end the last, and architecture means and behave. Okay, so now let's change the entity name. So now this will be UART_TX_TB. Now copy this UART_TX_TB and replace this entity name here and here. Now define the generics here. So our data width will be 8 here. So this is 8. Now our system clock frequency is 50 megahertz. So write it 50 megahertz means 50 000 000. Now our TX baud rate is 115200. Now because this is a test bench, so we are not needing port declaration here in this case, right? So I will remove this part from here. So this is our library declaration and this is our entity declaration for this UART_transmitter test bench. Now we will write the architecture part. So first we will define the component here. So what I will do that I will go to this UART_TX module and then I will copy this part from here. So this is our complete entity part, right? Now I will go to this test bench file and then paste this entity in this declaration section. And now I will replace this entity keyword with component keyword. Now copy this and replace this and UART_TX with and component. So this is our component declaration. Now I will copy this once again and then I will paste this after this begin keyword. And now I will give the component mapping for this UART_TX. So first I will give it some name. So this is our UUT, means unit under test, colon. So this is the component of UART_TX. Now remove this is keyword. Now write generic map. Now this TX_data width is connected to the TX_data width of this test bench module. Same, this TX_system clock frequency is our TX_system clock frequency of this test bench, comma. Now this TX baud rate is our TX baud rate of this test bench. Okay, go down. Now remove this semicolon from here. Now port map. Okay, so now this clock will be connected to the clock, comma. Now this reset will be connected to the reset, comma. Now this TX start will be connected to the TX start, comma. Now this Tin will be connected to our TX_DIN, comma. TX_Dout is connected to our TX_Dout. TX ready will be connected to the TX_ready, and then bracket closed, semicolon. And now remove this AND component from here. So this is our component mapping of our device under test or unit under test. Now first declare all the signals in the declaration part of this architecture. So we have these signals here. So I will copy this and then paste here. Now these all are the signals here. So let's declare them as signal. So these are signal. And now because these are signals, so there is no input and output. So let's move. Okay, now out. Okay, so let's see. So remove this signal. So this is extra. So this is signal clock, std underscore logic, signal reset, std underscore logic, signal tx underscore start, std logic, signal tx10, that is std logic vector, tx data width -1 down to 0. Now we have tx out and tx ready as an std logic, right? So this is good. So what we have did till now, that we have imported our UART underscore transmitter module into this Testbench module. And now the main part come, and that is driving all the inputs with our test scenarios, right? So first I will drive my clock frequency according to the 50 megahertz clock cycle. So this clock will be our not of clock after 10 nanosecond. Now to use this statement, I have to initialize this clock signal to some initialized value, right? So suppose this is started as an 0 value, okay? And it will get inverted after 10 nanosecond. So this is the clock frequency of 50 megahertz, right? And now we will write the process to drive these three input signals, that is reset, transmission start and transmitter D in. And we will get the output at this tx underscore d out and this tx underscore ready output, right? So we will write the process. So first give it some name. So this is test process. Now process. Now because this is a test bench and we are going to use wait statement here in this process, so I will not use any sensitivity list here. So simply start with begin keyword and in the last and process. Let's write the wait statement as well. And now we will drive our input signals, right? So we will start from the reset condition, okay? So at the very starting, our reset will be high, means reset is asserted, right? So reset gets a value of 1. Now let's define the other input signals at the reset condition as well. Suppose at this reset condition, our tx underscore start signal is 0, okay? And our tx underscore d in is, so I want that all the bits must have to the default state, which is 1 in our case, right? So I will write that others are 1, right? Now I will wait for 100 nanosecond. So wait for 100 nanosecond. Now what will happen after this 100 nanosecond? We will come back from the reset condition, means our reset will be 0, okay? And now wait for another 100 nanosecond. And now this is the time when I wanted to load our D in data into the transmitter module, right? So what I will do that I will drive this tx underscore start with the value 1. So this will be 1 and we will give some data to our D input, right? Means our tx underscore D in will be, so give any data here. For example, I am giving hex double A, right? Semicolon. So this will be 10101010, right? So this is our input data. Now our synchronizer module was synchronized with the system clock frequency, right? So instead these two lines directly after 100 nanosecond, I will prefer to wait for the rising edge of our system clock frequency, right? So I will write the statement that wait until rising edge of clock, okay? Means at the starting of simulation, we will apply the reset condition and we will also set these two input ports to some default state. And now we will wait for 100 nanosecond and after this 100 nanosecond, we will come back from the reset condition. And now we will wait for another 100 nanosecond. Now after that, we will wait for the rising edge of clock signal. And now when it happens, then our tx underscore start will be 1 and our D in data will be 10101010. Now we want this data for 1 clock cycle, right? So what I will do that I will wait for another rising edge. So wait until rising edge of clock. Then this tx underscore start signal will be 0, okay? And our D in input is set to the default state. Okay, so I think that's done. So let's quickly review the VHDL code here. So we have this library declaration, then we have this entity declaration, and we have defined the generics. So our TX data width is 8, our TX system clock frequency is 50 megahertz, and our baud rate is 115200. So this is good. Now come to this architecture part. So this is the component declaration and this is the signal declaration. So this is good. We have also initialized the clock signal. Now begin keyword. So first we have derived this clock signal at 50 megahertz. So we are inverting this clock signal after every 10 nanoseconds. So this is good. Now in this process we are driving these three input signals. So these three input signals. So at the very starting we have this reset condition and we have also reset this tx underscore start and tx underscore d in. Now this reset condition will be applied for 100 nanosecond. So after that our reset condition is 0 and now we will wait for another 100 nanosecond. Then we have waited for the rising edge of clock signal and then we have given the tx pulse. So this tx start is 1 and now this txd in is getting the value of x double a, means the value is 10101010. Now we have waited for the another rising edge and now our tx start is 0 and txd in is getting the default bits. And now at the last we have used this wait statement and then AND process. And this is the component mapping of UART underscore transmitter module. So let's save this code. Now go to this model sim simulator. Now we will import this file into this UART transmitter project. So right click. Now click on add to project. Then select this existing file option. Now click on browse. Now we have the separate folder for this Testbench under this UART project. So we have this Testbench folder. So open it and we have this UART underscore tx underscore tb file here. Select this and now open it. Now click on OK. Okay, so you can see this Testbench file is listed here. Now right click. Now select compile and then compile selected. Okay, so we have one error and it is saying that at line number 42 it is expecting semicolon, right? So go back to our Testbench code and let's move to the line number 42. So the compiler was complaining that we have missing semicolon, right? So you can see that we have missed to add semicolon in the last of this signal. So let's add this semicolon. Now save it. Now go back to the model sim simulator. Now close this. Now we will recompile our Testbench. So right click, now compile and then compile selected. Okay, so we have another error and that is at line number 85 and it is saying that it is expecting comma or something, right? So go back to our VHDL code and look at this line number 85. So line number 85. So this is the line number 85 and we have missing comma here. So let's add it. Now save this file and go to this model sim simulator once again, close this. Now right click, compile and then compile selected. Okay, so you can see that we are clear from the syntax error and you can see the right tick here and we can also see the message that UART transmitter was successful. That UART underscore tx underscore tb dot vsd was successful, right? Okay, so let's move to the library tab. And now we will look for the work library, right? So this is our work library. And now we can see this UART underscore tx underscore Testbench listed here. So I will right click here and then click on simulate. Okay, so let's move to this waveform window first. And then I will select this UUT from this instance window. So you can see we have Baud Clock instance as a component here, Serializer as a component here. If you want to expand them, so you can do that as well. So we have this Baud Clock instance and inside this we have these three processes. And for this Serializer instance, we have this Serializer process, right? Okay, so let's collapse this and just select this UUT. Now you can see that all the objects are listed here. So I will select the important one. So clock is important. Reset is important. This Baud clock is important. Now we have this input signal, so that is important. We have this output, so that is also important. We can also select this tx underscore packet. This is tx ready, so that is our output signal. So we'll select this, and this is tx underscore start, which is our input. So I will select this as well. Now I will just simply click here and just drag and drop here in this waveform window. Now suppose I wanted to run this simulator for 200 macrosecond. So give it the command that is run for 200 macrosecond, right? Now go to this waveform window and now zoom out little. Okay, so let's jump to the starting. So before we review this waveform window here, let me give you some key checkpoints which we are going to test here in this waveform window. So first we will check the clock frequency. So that must be 50 megahertz. Means the time period of one clock cycle will be 20 nanosecond, right? So that is one thing. Then we will check our baud clock, or you can say that baud clock pulses. And because we have 8-bit data at input D in, so we are required total 10 number of pulses at the baud clock, right? Because 8-bit is data, 1 is the start bit and 1 is stop bit, right? Then we will check our serial output and we will ensure that our start bit is transmitting first, and then one by one our data bits will be transmitted, starting from the LSB, which will transmit first, and then MSB, which will be transmit last. And then in the last, stop bit will transmit, right? And then once we test that, we will look for the baud rate. And because we are using baud rate of 115200, so each bit must be transmitted at the time gap of 8.7 macrosecond. Means the bit period of our baud clock must be 8.7 macrosecond, right? So we will check all of these points with the help of this waveform window. Okay. So first we will check the clock frequency, that is 50 megahertz or not, right? So for that we will zoom in this view. Now we will click here. Now we will add one more marker. So we have this another marker here. Let's zoom in a little more. So this is our first marker. Let's create another marker. So this is our second marker. Okay, so you can see the time gap of one clock cycle. So this is our falling edge and this is our next falling edge. And this is our one clock cycle. And you can see that this is 20,000 picosecond, means 20 nanosecond, right? So this means our clock frequency is correct, that is 50 megahertz. Okay, so let's zoom out little and now let's go back to the starting. Let me expand these names so that we can clearly see them. Now come back here. Okay, so come back to this point here. So you see this point here. So this is our reset condition. So before this line, I mean at the left hand side of this marker, so this section, that is our reset condition. So you can see that if I move this marker to the left hand side, then we have this reset condition high, and at the same time we have D in as a default value, so all 1. So remember we have make them all 1 in the test bench, right? And we have this start signal as 0 as well, right? So these values were coming from the test bench. Okay, so let me arrange them in a better way. So now this arrangement looks much better. So we have all of these inputs listed here. Then we have TX packet. Then we have this baud clock pulse. And in the last we have these two outputs, right? And now we can visualize our waveform in a better way. So let's move to this reset condition. So before this we have this reset condition. So when this reset is high, we have reset is equals to 1. Start signal is 0. D in is all 1. So our packet is this value. So this one is our stop bit. This is our data bits and this is our start bit. So this is good. So you can see that this reset condition is applied up to 100 nanosecond. So this is the marker for 100 nanoseconds. So you can see that this is 100 nanosecond near about. So here, right? So you can see that this is the line which is separating our reset condition. So left hand side is our reset condition, means reset is asserted here at this time period, and after this point reset is removed. So you can see that what is happening here. So till this point, till this 100 nanosecond, we have this reset condition, means this is high. Our start signal is 0. So this was our input. Our D in is all ones. So this is our transmission package. So this one is our stop bit. So these are data bits, and the last one is our start bit, and our D out is at the default state, right? So you can see that this reset condition is up to this 100 nanosecond. And after 100 nanosecond, we have removed the reset condition. So you can see that at this point, our reset is become 0, right? So this reset is 0 here, okay, at this particular point of time. And at this point, our start signal is also 0, because after reset, we have waited for the another 100 nanosecond. We have written this in our test bench, right? So we will wait for another 100 nanosecond. So this is the time, or this is the point when we have covered 200 nanosecond, right? So this is the first 100 nanosecond, and then this is the another 100 nanosecond. So after that, we have waited for the first rising edge. So after this point, our rising edge of clock signal is here, right? So let me zoom in. So this is our 100 nanosecond after reset. So this is our reset, and this is our 100 nanosecond after 8. And this is the falling edge of clock signal, right? And the first rising edge is at this point, right? So at this point, what is happening? The first change is in the start signal. So this is 1 now. Means when this 1 is given to this start pin, then our D in data will be 10101010, and now this data will load into the transmission packet. So this will become 1. So this one is stop bit. Now 10101010, and then 0, which is start bit, right? Now this start condition will happen up to 1 clock cycle. So at this point, this TX start is asserted, and at this point means just for the 1 clock cycle, and after this start signal is 0. So now this start signal is 0. This means that from now onwards, this data, this 10101010, or you can say this transmission packet, this value will start transmitting over the D out output, right? So you can see that we have this TX ready output. So at this point, this ready signal is 0 when your reset is high. And now when you deasserted the reset signal, means reset is equals to 0, then your ready signal become high. Means now this transmitter is ready to take any input from D input. So this is high all the time up to here. And this is the time when you applied this start pulse. Means your input data, this data is loaded into the transmitter module. And from this point, your transmitter is start transmitting the data, right? So you can see that at this point, your ready signal become 0, because your transmitter module is now busy in the transmission of data. And now it is not ready to capture any new input until all the data is transmitted, right? So you can see that we have this D out, that is 0 here, and that is our start bit, right? Now we will see that how many pulses we have at this Baud clock. We are expecting total 10 number of pulses at this Baud clock at the bit period of 8.7 microsecond, right? So let's zoom out little and let's see if we have 10 pulses or not. Okay, so let's count these pulses. So this is 1, this is 2, then 3, 4, 5, 6, 7, 8, 9, 10. So this is good. Now let's check the output, so which is D out. So remember what is our packet data? So that was 0, which was our start bit, then our LSB, which was 0. So this is our start bit up to here, and this is our LSB, which was 0. So you can see at this D out signal, then we have this 1, then 0, then 1, then 0, then 1, then 0, and this is our MSB. So that is 1. And this pulse is 1, and that is our stop bit, right? So our data was 0, 0, 1, 0, 1, 0, 1, 0, 1, 1. And now this is the ideal state. So you can see that up to this point our ready signal is 0, means it is busy in transmitting the captured data. And at this point all the bits, I mean 10 bits are transmitted. So now this ready signal is high, means now it is ready to take another input data for next transmission. Okay, so this means our transmission ready signal is also working well, right? Now we will check the bit period of this Baud clock signal, and we are expecting that must be 8.7 microsecond between two successive pulses, right? So this is one pulse and this is next pulse. So let's create another marker and let's move to this successive pulse. Okay, so you can see that these are two successive pulses and the difference is near about 8.7 microsecond. Okay, so this is in picosecond. Now this is in nanosecond, means 8720. And now if you convert it into microsecond, so this will become 8.7 microsecond. Now you can see little variation here because these markers are not exactly at the same point. So that is why there is little variation in the values, but this is near about 8.7 microsecond, right? Okay, so that completes our UART transmitter module, and this is the one part of our UART project because UART is also having one receiving module. So this is our UART transmitter module, and I am pretty satisfied with all of the results, right? Now, if you want to test it more, then you can write more test sets into the test bench for this transmitter module. So what you can do that you can jump to this VHDL test bench code and then you just need to write more test scenarios here in this process block. For example, you can import the text file which is having different test sets and then you can process it one by one into the waveform window. Or you can simply use a loop and that is having different set of inputs and those can be captured into the waveform window, right? So that was our complete UART transmitter module and we are pretty happy with the simulation results. So now this is the time to design the UART receiver module and its components. And finally, we will merge UART transmitter and UART receiver for the complete package. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.